Yeah.
Zhigang, you are muted. Okay, go ahead.
I think that long time ago, I don't know, it's 2012. I wrote an email to you. I said that I was complaining. I have a paper that's getting rejected by physical review letters. I was complaining that why our mechanics community does not have a lettersized journal. And then you said you can create one. And then and then we have this meeting in Illinois, and Tim was there, and I talked with Tim, right?
There was the summer school, I believe.
Summer school, yeah.
Summer school in UIUC.
Gen4 summer school.
Yeah.
Yeah, we started talk about that during that meeting with three, right? And then at the very beginning, we'll talk about whether or not this should be a mechanics letters or nanomechanics letters. Yeah. Maybe Ten knows a little bit more about this. I cannot.
I remember it was my initial memory about the how this started was at that summer school, Gen4 summer school at the University of Illinois, and I remember it was after the long day of a program, and we had the dinner, and then we went to Jimmy's house, and Jimmy surprised us by playing a nice piano piece first. Then we started the brainstorming session in a nice sunroom about this. We don't have the EML name at that time. It was about shall we try to launch a new journal for mechanics journal, a letter-sized journal. At that time, name of the journal was not the issue. It's about shall we do this, or what kind of journal shall we focus on if we decide to do so. Yeah, I think I recall the brainstorming session from there.
Yeah. Zhigang, what was your first recollection of the first encounter to this concept idea?
I remember that. I can answer that for Zhigang. I think that after that, we have a US NC 10 meeting in Penn State. Mm. And of course, I was a host for that meeting, organizer also. And Zhigang, Huajian, and Ten, all the people came. I think that that night I invited Zhigang and Tinju, my buddy in Georgia Tech, in my house. I think Ten also.
I was also there.
I was there. So we four started to talk about this. I think this is the first time that Zhigang getting in very quick, very enthusiastic about this. We started to debate the name. So Zhigang said, "Okay, let's do that." Right? I think that later on you have some kind of conversation with Zhigang and convinced him this is things that we must do.
What's your recollection, Zhigang?
Yeah, over the years, we always felt mechanics need to have a letter-sized journal. Many people talk about it, and we just keep talking. Nothing happened because it's just a new style of communication. The long papers still have this position, but young people need to have new ways of express themselves. So I was enthusiastic about the idea. I wasn't so enthusiastic to become an editor. So Jimmy, of course, was an old friend and very persuasive. I ran out of excuses. Then I had a brilliant idea. I said, Jimmy, you were a buddy of Zhang Rogers. Why don't you invite him? I thought Zhang would never do this. And Jimmy persuaded Zhang. I didn't know how did you do this?
See, John and I collaborated on a number of different projects. So we saw each other from time to time. And he's always been very interested in the mechanics part of these flexible electronics devices and so on. So when I told him about the idea, he's actually quite enthusiastic. And so I remember 3 of us then had a meeting, a phone call of some sort, and say, how should we do this, whether this is the right format or not. Then after the journal was launched, we had regular team EML meeting. And we talked about citation or impact factor repeatedly. And there's one time John mentioned something that I can never forget. Zhigang, you and I were in the mechanics community. We're thinking about a journal with an impact factor of maybe 3. Something like that would be very happy, right? And John mentioned that if the impact factor of the journal is lower than 8, my students and postdocs would not be interested. That was eye-opening to us. So certainly this, I think, this is to the credit of the authors and the contributors and and the editors of this journal. We're doing reasonably well, but we still need to work hard. By the way, I think one beautiful thing that we have been able to do is this great idea of EML webinar. Maybe let me see, I had it open somewhere. I don't know where it is now. So this is an idea Zhigang started. Maybe let me share if I can find that screen.
Yeah, please go ahead.
Doesn't look like I can find the screen. For some reason, I don't know. But that's not important. I think the important thing is, Zhigang, you had the idea. And I was going to share the screen of your little opinion. So this to read is human, to watch divine. Maybe tell us about how that started.
Oh, this phrase started. Yeah. So of course there is an old saying by a famous author, I forgot who said to err is human, to forgive divine. That was old. So there were just random thoughts. I saw my 3 grandchildren. The moment you allow them to watch TV, they just become so quiet. And each little face, just like angel, they watch. And they're very small.
Here it is. Do you see it?
Yeah.
Okay. Go on, continue.
Yeah. Well, that was there. Oh, so the start. Well, in hindsight, of course, it was not such a a remarkable idea to have a Zoom meeting. Right. So we were probably just, EML webinar probably was earlier than a lot of other webinar just by a few days. Because by that time we started in China, there are already many online meetings. United States just 2 or 3 months later in terms of shutdown. The moment we shut down, that was during semester. Then everybody at the university had to learn to use Zoom in a matter of 1 day or 2. You have no option because you're in the middle of teaching. In my case, I used Zoom a little bit before, just as interaction with companies. Companies like to use Zoom. So I had some idea how Zoom worked, but never used webinar, this kind of thing. Then at that time, just by coincidence, this guy I mentioned in the piece, Professor Wei Yujie, he invited me to give a seminar to his Institute of Mechanics in China. It wasn't wild success, so we didn't know what we were doing, but it was immediately clear this was already better than ordinary seminar in terms of reach. It's just, but if you only want to get a seminar, this is actually better than live seminar. So that's how I feel. So the second day I wrote email to you, Zhang, and you. You said immediately, right? Within, I guess, 5-10 minutes, I actually recorded all the time. And the decision was made. You actually suggested a name called EML Webinar. Initially, I had some longer name. You said I'd make it simple. So that was that.
Then I remembered Teng actually made it into an art piece. So how did you come up, Teng? How did you come up with those ideas? You know, the webinar, Zoom webinar is live, but recording, then people can watch it later. And maybe, you know, all these things. How did you come up with those ideas?
Yeah, actually, so the Zoom as well as a couple other this platform. I forgot the name of that. This basically a platform widely used. So Zoom is widely used in US and also probably in Europe as well. Back in China, I think they have another platform more popular than Zoom. But anyway, all of a sudden, the whole world, especially in the academics, and when you make the presentations, form the meetings, you have to go virtual. So we are all forced to do something like this. But then you see that everyone has a very full packed of Zoom meetings in your calendar. You cannot be there all the time. So then naturally is to archive the videos in a place, then people can visit and view the recording at a more convenient time. Some people may prefer to, enjoy a cup of coffee, sitting in the couch in the late night or early morning to watch the favorite video. Just like the other day, like Zhigang posted his this mechanics video. I saved the video until the weekend. I can enjoy it in my backyard instead of watching it on the same day. So then we had this idea. Okay, why not we archive all the EML webinar video in YouTube channel, because it has the probably the most availability to most people in the world. Then for people who cannot view the YouTube channels, we also found another channel. So with these
This
two
is
channels,
Chinese Weibo.
yeah, the Weibo. So we post a video there. Then almost majority of the population in the world, if they are interested, they should be able to have access to EML Webinar. And in the back end, I can see those EML Webinar archives. The viewing is been steadily growing. Okay, it's not like okay, we have a lot of views right after the real meeting, real webinar. It's constantly increasing. It slows down, but it's steadily growing because more and more people get realized. Oh, there is a. It's like the gem. They found the gem. Oh, there is a tons of videos over there, very long, but with a lot of informations there, and typically also not available in other format of webinars, especially like the Q&A session. I think that's, we mentioned quite a few times that the Q&A session of EML webinar is a unique thing there. And we all ask good questions, and the speakers, they give answers. Those kind of Q&A communications are not typically there in conference setup, or even nowadays in a webinar setup. I think that's what we are famous for, part of the reason. Yeah.
Thank you, Tong. So Zhigang, we have a few minutes. Maybe yeah. I can ask you your own career path a little bit. You started with essentially hard materials.
Yeah.
Fracture, interfacial fracture. At the time, composite material was very popular. When did you get into soft materials? Why did you get into soft materials?
Yeah, thank you. So, right, my thesis I did my thesis with John Hutchinson, working on interfacial fracture. As you mentioned, the initial motivation was composite, ceramic matrix composite. So I did calculations. These calculations, when you do fracture, inevitable you have to interact with experimental colleagues. And then I noticed Tony Evans, that was one of the experimental colleagues, was also interested in electronic packaging. So plastics, semiconductors integrate together, and of course, interface is a big deal. So very early on, I got into packaging. And it's by pure luck. There was one person, his name is Chin Ma. He sadly passed away a couple years earlier, cancer.
Was he at Intel?
He was a postdoc for David Clark at Santa Barbara. So he took my courses, fracture mechanics, plasticity. He liked mechanics. He was a material scientist, a brilliant material scientist. And then he found mechanics is useful. After he went to Intel, he engaged me, gave me money, gave me ideas to work on these. One of the hottest things during those years in the 90s was something called a low K dielectrics. Some low permittivity dielectrics, some of these materials are plastics. So suddenly I realized at Harvard, it was at that time when I was trained, it were all metallurgists. Metallurgy knew practically nothing about polymer. So that was the beginning point. Starting working with Intel, working on plastic, then become softer, elastomer, become hydrogel. Of course, when I went to Princeton, the hottest thing that was in 90s. The hottest thing they tried to get started was the stretchable electronics by Sigurd Wagner. So Sigurd talked to me, I told Seeger, he was an electrical engineer. Oh, I work with Intel. I was very proud. He said, well, why do you work with Intel? Intel is shipping off all their manufacturing to Asia. If you want to stay in the United States, you need to start something else. Yeah, chip becomes smaller, but people do not. We need to have large screens. Let's work on large area electronics. That was a name for stretchable electronics at that time. Yeah, soft materials, learned from application. Then gradually, of course, soft materials has such a deep physics and chemistry and other applications, including human being. Just endless game, endless game.
So, Zhigang, my recollection of our interaction is you have always been a very original researcher. The problems that you think about, the questions you ask are very fundamental and very original. How do you select these projects, research projects to work on?
Yeah, well, so how do I select? I told my students, right? So I don't play any sports, but I imagine how sports are played. I said, you need to keep trying. Try to kick the ball into the gate. Keep trying. Maybe you miss some, but a few may hit. You just keep trying. So I have all my students know, I have a long list of problems, random thoughts, about several hundred entries. So once you have a long list of ideas, you can keep trying. Keep trying this. You have students, keep trying. So some of them work, and yeah, Chang Hui is here. Chang Hui is just incredibly original. And all you need to mention initially one idea, he will not only finish that idea, multiply that idea into many, many. So I guess you also need to try people. Some people just like that.
Great. Let's continue our conversation after your talk. Maybe Zhigang, can I ask you to share your slides?
Yeah, I'll do that.
So, meanwhile, let me introduce you. This is the EML webinar series, and my name is Hsia. I'm at the Nanyang Technological University in Singapore, or NTU Singapore. And we have the great pleasure to have Professor Zhigang Suo of Harvard University to give today's EML webinar. Zhigang doesn't really need any introduction. He's actually a co-editor-in-chief of EML, but there's something interesting about the short bio he wrote. Of course, he's the Alan E. and Marilyn M. Puckett Professor of Mechanics and Materials at Harvard, and he grew up on the campus of Xi'an University and graduated with diploma, I assume, from its affiliated kindergarten, elementary school, middle school, and high school, then university. So he never got out of the campus for a long time. He wrote his undergraduate thesis on coupled boundary and finite element method under Professor Xin Ji at Xi'an University in 1985. Then he wrote his PhD thesis on interfacial fracture mechanics under Professor John Hutchinson at Harvard in 1989. Zhigang joined faculty of the University of California, Santa Barbara in 1989, Princeton in 1997, Harvard in 2003, and he writes papers under students and collaborators. I've known Zhigang for a long time, since our student days, and certainly many things have changed. Our hair are getting less and less, but one thing I think that has never changed is Zhigang has always been a very original researcher and very passionate, enthusiastic. Actually, his passion is infectious. So it makes people excited. So today, we're very glad that he's going to present something that he's been doing recently on topological adhesion. Zhigang, the floor is yours.
Thank you, Jimmy. Thank you, everyone, for coming. So today's talk really is about this diagram. So this blue circle represents a polymer network. And here is another polymer network. What we're trying to do is connect these two blue polymer networks through a third polymer network. This is a yellow polymer network. And I'll show you why we're doing this, why this is interesting, what are the new mechanics and physics, chemistry we're trying to learn. And applications. So that's a topic. So yeah. So the now first just one slide or two about this wet elastic materials. So these two young men really made elastic and wet materials very real to me. So this is Kaplinger. He is now director of Max Planck Institute, and Jianyong Sun, he is a professor now at Korean Seoul National University, and two other people. Everybody, of course, know Whitesides. So these two guys were postdocs in my group when they did this work, but they taught me about this hydrogel, this material. This material, now here's a real material here, transparent material, very stretchable, and it's wet. The constitution of this material is, it has a polymer network, so that's elastic, and it has 90% water, so it's wet material. It's like a jello, tofu, this kind of material, but some of these materials are very stretchable. Tofu is not particularly stretchable, but you can find a hydrogel easily. Very stretchable, stretch 10 times even, like rubber. Now, because of water, 90% water, you can dissolve ions in this hydrogel. So it's an ionic conductor. This material is a conductor, stretchable, transparent conductor. So these two people said, how can we make use of this? So now here you need to make a device. This is our, later we call this kind of device Inotronics, because it combines ions and electrons to make it work. Inotronic, the word itself perhaps is not even new, but it's not a popular idea yet. But we felt this is the 13, right? It was already 7 some years. Now we felt that may hit one of the most fundamental problems in our time, really literally in our time. So our time is characterized, of course, we have always been characterized by ionic materials, ions, because our nerves have a lot of ions. That's how nerve works, right? So this nerve technology has been around for maybe 1 billion years. This electronic technology is very new. It's almost like a Band-Aid for human beings, right? You connect each other through electronics now. Very new, about 100 years of history. So in recent time, of course, people want to connect human with electronics through internet, through cloud, right? The interface now is very primitive. We all know that, right? You have to type, and now we speak, you see videos, but you don't really monitor your body parts constantly, and also record your thoughts constantly. Why not, right? So there are a lot of people working on this kind of technology between human and between cloud and other humans. Now, if you need to do this, it need to make essentially you need to have electrons. So this is the metal, that's the electrode, and the electrolyte is a hydrogel. Hydrogel has ions. So you have this interface between ions and electrons. In order to have a long-last application, this interface need to be secure, well adherent. Also, electrons and ions should not react, should not have a chemical reaction. Otherwise, this interface is not stable, right? So it turns out it's possible. Historical people know about this. About maybe 100, 200 years. It's known. It's known. So now the thing is now looks like, so I felt it's kind of like a semiconductor technology in 1950s. People begin to know physics, but we need to have engineers and creative inventors to make things happen, right? From physics, chemistry, to some useful things to human. So I think that's not just I, a lot of people think this way. So Inotronics is one of the hottest words at the moment. All right, so, so as some demo, well, now here's the demo we made in that paper. So here's a hydrogel ionic conductor we use as an electrode to on the two surfaces of this elastomer. This elastomer is insulator and it's transparent. You already see hydrogel is transparent as well. And then we can apply electrical voltage to the top and the bottom electrode. So you apply voltage to an dielectric, it can deform. So that's a video. So you can see, we apply cyclic voltage through a, essentially through a computer. You can cause mechanical motion. So the experiment is keep the voltage amplitude fixed, but increasing the frequency. You can see there's a beautiful mechanical experiment, right? Vibration patterns. So we also saw resonance. As frequency goes higher, the pattern becomes more refined. And the pattern eventually kind of disappeared. The amplitude became too small eventually. But you hear the sound. That's a small amplitude vibration cause air to vibrate and pass sound to you. So then this is a loudspeaker, right? You apply electrical signal and come out with sound. So these guys are very clever. This is this idea belonged to Kempliger, Christoph. He is an avid musician. So he made this happen. He made Ionic music. We call them Ionic music. It's an iTunes. So what it does is we have this device. This device was fed with using computer to fed a voltage signal, and voltage caused the membrane to vibrate. Vibration generates sound, and you hear the sound. We record the sound, and you can see this loudspeaker. There's a piece of hydrogel elastomer is fully transparent. Beautiful piece of device, and musical quality is pretty good. We haven't, I don't know enough about sound quality, how to test them. Which is good enough for us. And so now, but there is an unpublished video associated with this. We find interface. We have to glue hydrogel to elastomer without any glue. Because if you have a glue, you stop electricity, right? So it's attached. That attachment adhesion is not very good. So you can see from this video. So you can see the vibration. Vibration is caused by cyclic voltage. You can see debonding. The hydrogel downs off elastomer. The adhesion is just a van der Waals interaction. We did not publish this. We said, okay, if we try this thing a little bit, adhesion become better. It's not great, but at least it doesn't do this complete the demonstration. That was good enough for the paper. But there was a chemical engineer, I forgot his name, called me immediately when this paper was published. He asked me, Professor Suo, how did you make hydrogel stick to elastomer? I did not even know that was a problem. I immediately called these two postdocs. How did you do this? Oh, Zhigang Suo, that's Zhigang Suo. Zhigang Suo is really a brilliant material scientist. You know, oh, I just use an air blower to blow the air of hydrogel. So hydrogel surface is kind of dry, and I just put it on. That seemed to be better adhesion. That was that. That was that. So of course, so you just heard I wrote my thesis with John Hutchinson decades ago on interfacial adhesion. That was my thesis. But back then, interfacial adhesion meant ceramics and metal and semiconductors, never about hydrogel, right? Well, that was a new problem to me. So, and we, so that was a problem. We didn't have a solution, but we're engineers. We don't have a solution. We just charge. Yeah, I promise that this will getting better. I don't know what's the problem with the computer. Anyway, so we made additional devices. All these devices have very weak adhesion at this point. Of course, we never demonstrated weak adhesion. We just show device kind of work. So this device is a pad, so that because you have electrical conduction, and it's a stretchable, transparent. You can put on glove or directly in contact of skin. If you push this, you will have a signal coming out, electrical signal come out. So, and the device involve a dielectric elastomer in the middle and hydrogels here. And eventually you need to transmit that electrical signal to a computer. That means to the electron. So ions need to influence the electron through electrical charge as the interface. So all these interfaces are critical for the mission. But we didn't know what to do. We just stuck together, pray it works good enough for a photograph. And then we move on. Because at that early stage, so every paper is very original. Nobody did anything about this. So the claim it might work at least for a couple of hours. So that was a spirit at that time. Oh. And then this is very interesting. Yeah, this is Cang Hui Yang. He's a new professor now at he's a rapidly growing new university in Shenzhen, SUSTEC, new professor. Anyway, he was a student. He was late to the game, but not too late. By his standard, it was late because he did not invent the first device. At that point, he was a new PhD student. He said, my PhD thesis will be developing all possible inotronic devices. He literally published 10, 20 papers. Each one is very original. Just a little device, a little device, a little device. So here's one little device, very interesting, picked up by many people now. We say, so we had some superficial knowledge of how human axon work, right? Axon. So let's say this is your brain make a thought, right? When brain makes thought, it doesn't really write down, right? It generates electrical signal. Let's say this thought is command the feet to lift up. Feet is about a meter or two away. So, so it's an electrical signal transmit down to the feet, not ion itself, but electrical voltage, very rapid. You can measure yourself. The speed is more than 100 meters per second, very rapid. This computer is unstable. This is today new problem. I didn't know what happened. Okay. So, and of course, for people who know biology a little bit, even we knew this. The ions are more than just electrical signal. But for a bunch of mechanical engineers, let's just do electrical first. It's easier. So here's our mimic. We say, all right, for the real axon, it's known, established for many years. You have inside is the iron. It's a salty water, right? There's iron inside, and also salty water body fluid outside. And there is a surface layer, a shiny surface layer. It's a fat layer. It has a name, myelin sheath. But it's really is a dielectric, just dielectric. It's known in the axon literature. All you need to do is look at the first or second page. Look at this figure. People tell you about this. It's nothing deep anymore. All right. So we said, let's just mimic this. So the mimic is very simple. We use a hydrophobic elastomer to mimic this shining myelin sheath. That's just dielectric. Electricity will, no charge carrier will go through this layer. All right. And then for salty water inside and outside, we use hydrogel. We don't use water. There's water flow around. It's not a decent device, right? We want to make a solid state device. That's our goal. Okay. And then the function device is very simple. I play music by applying a voltage signal here, right? And this voltage signal need to rapidly transmit to the other side, maybe 1 meter in distance. And then I connect voltage signal to a loudspeaker. Can I do that? Will this thing do that? Without all this chemical biochemistry, without this biochemistry, this, action potential, all these interesting things, people won Nobel Prize. Maybe we're not quite ready for Nobel Prize yet. Just do simple things first. It does. It works beautifully, works better than human axons. So here is a demo. Yeah. So here is our artificial axon with this elastomer hydrogel sandwich. And here is our musical signal, voltage signal coming from a cell phone. Here is our loudspeaker. So voltage signal pass through this and play out. Works very well. And it's a fully transparent, solid state. And it's stretchable. So this is a Chang Hui Yang here, and Bao Hong Chen. He is still a Harvard student. But the work was actually performed in Xianzhou University when both students were still there. This is a highly stretchable. So once you have this new kind of device, right, axon cannot stretch this way. It cannot be this stretchable. Eventually, these two students will stretch 8 times. And once you have a new device, you do new experiments. You say, oh, whether stretch will affect sound quality. And you don't need to have a high instrument. You can use your ears. You can detect. So to my ear, I cannot detect any difference as a stretch happens. It means you transmit high voltage, high frequency signal with high fidelity. Not a problem. Just ordinary hydrogel. The reason we can do better than axon in terms of frequency. So for human music signal is about 20 kilohertz. And our thing, we measured experimentally, electronically, we can pass 1 million hertz signal with fidelity. The reason we can do better is because our hydrogel has a lot more iron than salty water inside the body, orders of magnitude. We just put, so this is broken. Of course, after broken, you don't have signal. So that's a part of the experiment. All right, so that's wonderful. Now, there's another experiment. People want to do neural interface. Here, this is a new neuron, and you want to connect neuron with an electrical, let's say, computer. But the natural thing to do is use a piece of hydrogel, because the hydrogel has the same constitution, almost in constitution as neuron, with ions going in and out. And when ion go in and out over long distance, this ion can excite electron, attract or repel electron to turn this electrical signal. This distance can be very long. We actually did a demo with people in Zhejiang University. They're neuroscientists. We're just making this instrument. I won't explain how it works. It's actually a piece of very good work. So we're publishing Extreme Mechanics Letters. Now, this lead author now is a student at Harvard, and he decided not to do mechanics anymore. He really wants to do neuroscience. He's no longer my PhD student. I recruited him, but I respect his wish to become a neuroscientist. So he's doing something else now. But a brilliant student. All right. So now I need to keep back to interface, because that is a mechanics problem back in my mind I need to solve for new technology. So here's another reminder, the work, let me show you what we had. So we made a hydrogel composites very early on, independent of all these devices. So the transparent thing is a hydrogel, and the fiber are just steel wires. We use steel wires, wash pots, this kind of steel wire. We put into hydrogel. You can see when we pull this, you can see this steel wire is streaming along. It means you have interfacial sliding, right? You have interfacial sliding. So the interface bonding is not very good. You can see, oh, this guy just swim away. Oh, this guy swim away. So our interfacial bonding between steel and hydrogel is terrible. The failure mode is just sliding. The composite has an interesting property, but it's not quite useful. So that was another incident. Then around that time, there was a Nature paper published by extremely influential group, Libler group in France. And they created they actually knew this paper is a wonderful paper because it reviews the literature and made a step advance to bond tissues and hydrogels, wet materials. So the specific thing is interesting. They use nanoparticles of silica, but a silica doesn't form a covalent bond. It allows you some polymer adsorption. By this adsorption, they achieve adhesion energy. For people know about this kind of number, energy per unit area. Adhesion energy per unit area is about a 10. Now 10, I don't know if you guys have intuition about this. 10 is a very low number. It's like tofu, very brittle number, like a glass, like tofu. But even then, it's worthy of nature at that point. You can see how low the standard was, because this was hard doing wet adhesion. So now the way to measure adhesion, my group does this professionally. I have so many ways to measure adhesion, but this is one method I ask you to remember in your head. It's just called a PO test. Once you adhere to things, and let's say this green thing's unstretchable material, like plastic or cloth, and here is a piece of hydrogel, and you just peel it open. You measure applied force as a function of time. So initially, this crack does not grow, you just get a blunting. So you add more force, you will get a blunt more, and then at some point it become growing. when you start to grow, it reaches a steady state. This steady state force measures adhesion energy. What you do is a steady state force divided by the width of the sample. This becomes energy per meter squared. It's just Newton per meter. For people who don't have a sense number, 1 Newton is just weight 1 apple. So you need to distribute the weight over 1 meter long. That's not a very large force, tiny force, very brittle, or 1 joule per meter squared. All right, so that was the standard when we started at that time. So yeah, I won't bore you our failed, we did several years of failed experiment. We published a paper to record our failure. I won't bother to tell you that paper anymore. I will tell you why our understanding now, why we were doomed, or everybody else was doomed. For many decades, there was a enormous literature for more than a century, or actually dated to human history, using animal glues to bond things. Animal glues was not very strong when it is wet. It's not. And of course, now we understand why people should understand, but we didn't see it described clearly in the literature. We reviewed somewhere, it's published in 2018, this basic interpretation. So the question, why is wet adhesion so weak? That's the question, that's observation, but why? It's just water. The answer is just water. Now let's take a look. So if you use a dry adhesive, such as epoxy to bond with, or any plastic, to bond with aluminum, dry, right? So then every atom really form a bond, even though the bond itself could be just, could be just a very weak bond, like a van der Waals interaction, but everyone shares a load, right? Democracy, everyone shares a load, or even 50% shares a load, that's okay. Still a lot. But if you have a hydrogel, we said hydrogel 90% of water. So 90% water flows. So even first layer of water, let's say first layer of water bond very well with the substrate. Okay, 100% bonding. But your second layer of water still flows relative to first layer of water. So you can never win. So your adhesion energy essentially is limited by the adhesion between water molecules in liquid state. It's not much, right? So that's why you're doomed. You're doomed doing this. Okay, so we were doomed, but not everyone. So there was a brilliant paper. This is just a landmark paper by, this was a former student in the group, but he is now just such a brilliant professor at MIT. He did this work totally just after graduation, graduation many years. So this is really just his work with this brilliant student, Yuk and Zhao published many just great papers. So here's the paper. They just showed by demonstration wet adhesion can be tough. The idea is very simple. So if you now know their message, you can always go back to the literature. You say people knew about that, but people didn't say this clearly. They did. These pair of people, Yuk and Zhao. So the message is very simple. You cannot rely on water to have strong adhesion. You really need to engage polymer chain. So if you form a covalent polymer chain of the gel, hydrogel, with the substrate by covalent bond, then this bond is at least as good as the gel itself. And we already know gel itself is stretchable, right? Then this interface will be good enough, right? So this is one idea they had. That's fairly traditional in the literature. If you look at the literature, people just didn't say this clearly. But the other idea was very well known to mechanics people, but not really known to people, to do hydrogel. This is about dissipation. If you want to have high toughness, you need to build in some plasticity in your gel so that you have a strong bonding before bonding break, you will cause plasticity, you dissipate a lot of energy. So the combination of these two essential ideas allows them to have interfacial toughness reach more than 1,000, about 2 or 3 orders magnitude enhancement. By now we know you can go even beyond that. That's not even competition anymore. The method, the importance of this paper just says it's possible. You just need to do design, right? Okay, so that was that. So we were very fast follower. So this student now is a professor, Jianyu Li. He cannot be here today. He's teaching today at in Canada. He said, let's make a practical application. This is done with bioengineering group of David Mooney and Yus Vlasic. And these two students, two youngs, made seminal contribution, basic discovery of this. So here's a pick hard, and we use the ideas I just described, but now in a real application or realistic looking application. So this gel itself is very tough. Its self-toughness is more than 1,000. And you can see adhesion is wet and very elastic, so hard still moving, and adhesion is strong. You can see, you can use this as a spring, gel as a spring. The force is very high. We measured adhesion toughness is about 1,000 joules per meter squared. This paper got a lot of people's attention because this is a tissue adhesive. We already said for many, many centuries, people have been developing adhesive, elastic, wet and elastic adhesive with very, very poor results until this paper, literally until this paper. The application people identified for many, many years is an important application. Wound, if you have a wound in the wall, for example, or any other wound closure, and also during surgery, also drug delivery, very important to have strong adhesion. And it was not available. So I can show you, no, let me just show you basic chemistry in the mechanical kind of way to show you the chemistry. So the chemistry is interesting. We were the first in using this chemistry this way, but the basic chemistry is known. So what you do is the following. In tissue, it's well known you have a lot of the COOH group, functional group, all on the tissue itself is like natural hydrogel. So you have COOH group, and our tough hydrogel, we had previously developed tough hydrogel. I didn't have time to describe this tough hydrogel today. But inside this tough hydrogel, we also have a COOH group by accident. And this high toughness, for whatever reason, I don't have time to describe, essentially it has a dissipation mechanism, can have nearly 10,000 joules per meter squared toughness, very tough hydrogel. So now we use so this was discovered by these two youngs. You can use this polymer with this NH2 group. This NH2 group will react with this group, essentially form a bond called peptide bond. That is a bond in protein chains. All protein are peptides. Well, that's the same bond. It's a known chemistry, but this particular application, so far, nobody challenged us. This seems to be new. And this adhesion is enormous, 1,000. Yeah, okay. So that works. And this slide really shows this adhesion energy. This is our tough gel, adhesion energy about 1,000. And these are all the available gels people use for tissue adhesive. The best one is called cyanoacrylate. It's a crazy glue also used at home you can use it to rapidly glue anything, but it's plastic and it's actually poisonous. And all the rest are made of a protein. It's just terrible. The toughness is even below 10. Terrible. All right. So we break a record, and many people are doing this now. Many people, they're just way beyond my capability, because that requires biocompatibility applications. There's just too many things. I still collaborate with people, but I will not talk more about this because the mechanics is not very interesting anymore. You know you can do it. It's about engineering take a major role now. Okay. Now, let's summarize. We want to do mechanics, the rest about the mechanics. So if you want to make a tough adhesion, requires a synergy. So clearly you need to have a good bond. Xianghe reminded us, you need to have a good bond. But bonding to chemists, that's trivial. They have zillions of bonds. We just need to learn. That's good. Now, the other thing, it's known to all mechanics people. If you want to have a tough adhesion, not bonding itself is not good enough. For example, glass, window glass has covalent bond, but it's very brittle because it doesn't have plasticity to dissipate energy. So you need to have somehow building some dissipation mechanism. For mechanics people, that's a trivial idea, but to implement in real system, it's still an art. I'll show you a few examples later. So that's the mechanics. And this thing, this is a kind of new, people kind of know this, again, not well articulated. I guess we were the first people really systematically articulate this point. You need to have a topology. So this direct bonding is just one possibility to make connection. Another possibility is just using third network to make a link. You don't need to have a bond between these blue things. So this offers a distinct advantage. The advantage is, suppose your blue thing and this blue thing themselves do not have bonding, do not have, in chemistry it's called functional group, then you cannot just direct bond them, right? But what you can is you create a third thing to bond this. All right, so we call the synergy between chemistry, mechanics, and topology. I'll give you examples how to do this. Now, so first of all, simple idea. Of course, there are many ways you can connect things. Each way we call it a particular topology. So I just mentioned two basic things. One is a bond. You just have a direct bond. I will use a simple diagram like this. One network is represented by a circle, another network, another circle, black network, a blue network. The direct bond is represented by a dot. I also mentioned you can have a distinct topology. The blue network and the black network do not have direct bond, but you have a green network to bond them, right? So clearly works. So let's implement this. Here is our first implementation. So the idea, we call this idea molecular suture. So for having suture, you need to have a hole. So yeah, but because you have a polymer network, is full of holes. So each mesh is a hole, right? And a thread polymer, we have a nanoscaled thread. Each polymer is a thread. And you also need to tie knot. Without the knot, thread will pull out from the cloth. You don't have bonding, right? So not just you need to have a crosslink. So these are all clear chemical entities. Then once you can make it work, of course, you can have a topological entanglement. Topological in the sense you need to cut this network to separate. You cannot just separate it by pulling it. So you have a two pre-existing network, black, and then a stitching network, this red. So conceptually, there's nobody will argue this is a good idea. So we had this idea for some time. I talked to various people, how do we do this? people didn't do anything or didn't do anything successful. And this Jia Weiyang, he was a student in the group, mechanical engineer, student, learned enough chemistry to do this. And he's now a postdoc at MIT, Langer and Daniel Anderson group. He is doing bioengineering now. All right, so, but he was a mechanics student. He defended his mechanics thesis. All right, right. How did he, this was really his invention. Now, again, chemistry itself is known, but this use to do topological adhesion was entirely his invention. This is how he did it. So it's known in chemistry, in biology. The shell of crabs, has this polymer called a chitosan. And it's also known chitosan is a solution. In the solution form, dissolved in water when pH is 5. It's known chemistry. Jia just learned it from book. The way it becomes solution is when pH is low, you have a lot of hydrogen ion in the water, and that hydrogen ion attach to this NH2 group, makes this into an ion. And this ion essentially, you can say, is repels this ion, or however you think about this. It become essentially a salt. It's a polyelectrolyte, a salt with a lot of ions along the chain. That's pH equal to 5. However, when pH equal to 7, the hydrogen ion is lost, you have NH2 back. It's known this NH2 and OH form hydrogen bond. So this hydrogen bond is similar in the hydrogen bond in cellulose, essentially in wood, same kind of hydrogen bond. So all these things are known, and including this pH control was known. But Jia had the wisdom to turn this into this technology, or at least a demo of this topological adhesion. This is his idea. He prepared 2 pieces of wet material, in his case, just 2 pieces of hydrogel, very stretchable hydrogel, pH equals 7, pH equals 7. And he prepared this chitosan solution at pH equal to 5 and spread this solution on the interface. It's a liquid, you can spread on the interface, right? And then pH 7, pH 5, pH is just a hydrogen concentration, will diffuse. Once hydrogen diffuse into this place, and then you become it's called a complex, hydrogen bond complex. You make a crosslink. That's all, right? You create this red network. The network connect these 2 pre-existing hydrogel, right? So that's the concept. It really worked. So we just do measurement. Oh, wait a minute. Jesus. I'll show you. I deleted some page. I'll show you data shortly. It achieved toughness on the order of 1,000 joule per meter squared, depending on hydrogen, depending on hydrogel you use. I apologize. So I owe you 1 or 2 slides about the data, but believe me, it works. So now, but how it works? Now the idea is the following. It's interesting. It involves both diffusion and reaction, right? So you need to have a reaction to form new network. But Jesus, sorry, computer has some problem. Once you trigger with a hydrogen ion, it forms a network. But before forming network, the polymer chains can also diffuse into the network, right? So there is a reaction, there is a diffusion. So for any material scientists or mechanics people, You know, diffusion and the reaction process is crucial in many technologies, but very hard to model because it involves too many things. So we, instead of doing detailed model, we do experiment in this case, just using this picture, conceptual picture as a guide to do experiment. So there's some theory of the mechanics, but it's not very quantitative at this point. Okay, so now let's nail down this idea. So it's a reaction and diffusion both need to happen, but it cannot be too fast. One of them cannot be too fast. For example, if your reaction is too fast, before polymer chain diffuse into your network, you already reacted into a network, then you just have 3 networks without connection. Bad, low adhesion. Or if diffusion is very fast, the polymer chains already diffuse into the gels, and you don't have a network forming here. Again, there's no adhesion, right? And there's, of course, a happy middle ground you need to find. So initially, Jiahui spent enormous amount of time just to find this happy middle ground without theory, right? The theory is just this. Just say you need to tune. Okay, so now here's the experimental data to show this idea. So one tuning parameter is the pH value. You can control in your in the gel, right? You can prepare your gel with a pH equal to 1, pH equal to 7, pH equal to 12. If a pH is too low, you just have an enormous amount of hydrogen ions so that all your polymer chain cannot form bond, which just diffuse into the hydrogel. There's no adhesion. Adhesion energy, so there's a vertical axis, adhesion energy really low, no adhesion. Or if you have very high pH, very few hydrogen ions, your adhesion energy is also very low. The picture is like this. You mostly form network just in the middle. You don't really form extended network. So that's also not very good. And if you do this middle ground, pH equal to 7, you really have a peak. This peak is 150, really good peak. So I'll show you in what sense it's very good peak quantitatively. Now we have a system we can do mechanical tests, this peeling test, to allow us using peeling tests to study chemistry, right? So we don't have a theory, but we know good or bad by experiments. Okay. So, and just to show not only chitosan does this, we tried a number of other gels, alginate, PAS, cellulose. They have a very similar, signature peak, but the peak happens at a different pH depending on polymer. All these numbers, you just have to do experiment. So far, we don't know how to do calculation to predict where's the peak. So you have to, be a chef. Okay. So now you can study mechanics, ask mechanics question. The question is which network break? So remember you have 3 networks. You have, in our case, there's a polyacrylamide network. This is a pre-prepared network, very stretchable hydrogel, and another stretchable hydrogel, same. We want to use a chitosan to form a red network. So when we peel this cause breaking, so we can ask whether your polyacrylamide break, or your chitosan break, right? Experimentally, which thing break? And we can see this, right? By doing peeling tests. So we do peeling tests, we apply energy, apply load. Load divided by width is this energy released, joule per meter squared, and measure crack velocity. And you can see, we compare 2 cases. There's a blue thing, blue dots is just one piece of a polyacrylamide. You don't have chitosan. So then you really need to apply a high force to break this. But if you use a chitosan to bond this polyacrylamide, the force become lower. So this we take as evidence that we're breaking chitosan. rather than breaking polyacrylamide. Of course, on the interface, the breaking we cause a cohesive failure through the chitosan rather than happening along the interface or happen inside polyacrylamide. So we can ascertain this question, answer this question both by visually, by looking at a fracture surface, and also by data. Right? So another piece of data is very interesting. So, so these two curves are previous two curves. Now the scale is totally different. Remember, we have tough gel, right? So if we use chitosan to bond two pieces of tough gel, then the toughness becomes enormous. Of course, we know that. You don't need to change bond. You can use the same bond, the chitosan bond. All you need is having dissipation that can amplify your energy all the way to thousands, right? So that's what's happening. That's good. All right, now at this point, let me summarize what I told you. The point is the following. So in studying material science, we always study cohesion first. That's cross-linking within individual material. Cross-linking form cohesion. So if you cause bonding between two materials, blue material and a black material, you call that adhesion. Now we just invented this word into the dictionary, into the literature, haven't made into dictionary yet. We call it topohesion, topological adhesion. It's a distinct from adhesion and cohesion. You can do this. The topohesion is as strong as cohesion and adhesion, because in order to disengage, you need to break atomic bond, right? It's as strong. Okay, so that's great. Now, there's a problem. We did further discovery. It's very slow, very slow. So adhesion energy, we measure by PO test. We can measure it as a function of time after you form that adhesion. To reach this 100, 200, 300 adhesion energy, you need to have 50 minutes. That's bad. If you talk to surgeons about 50 minutes, then this cannot be used in surgery, right? Too slow. So the first question is why it's so slow? And can we make it fast? That's the next question. We recently got answer. The answer is yes, we understand why it's so slow, and yes, we can make it fast. So I'll go through this piece of physics with you. This is a striking hypothesis. This is a new hypothesis made us. I'll show you the hypothesis, and I'll show you the test of the hypothesis. Striking hypothesis. Hypothesis of a topohesion. Topohesion requires entanglement of only one mesh size. So what does that mean? So if let's say this is a black network, right? And here is my topohesive. All you need to do is connect or have an entanglement of one mesh size. Then in order to disengage, you need to break atomic bond. Having multiple mesh size doesn't really help you, right? It's very clear from this picture. So it means your polymer only need to diffuse about a mesh size on the order of 10 nanometer. You don't need to have a micron, 10 micron, you don't need that. Just 10 nanometer is good. So it's known in polymer, so I don't go through these, there's some deep polymer science going on here. But because the distance of diffusion is so short, even for long chain polymer, you just need to some milliseconds, less than a millisecond, you complete diffusion. So polymer diffusion actually is very fast. Diffusion is not a problem. It's a reaction that's the problem. It's a surprise to us. We did not anticipate this before. So, and then we say, oh, what is your reaction time? It's interesting in our case, in our pH-triggered topohesion. For pH-triggered topohesion, so it need to have a diffusion of hydrogen ions or OH ions. So you need to diffuse these ions. these diffusion need to diffuse across the thickness of your green material. In our experiment, as an adhesive, we put about 1 millimeter thickness. Even though individual ions have high diffusivity, the distance is just very big. That's way beyond atomic distance, molecular distance. It's macroscopic. That's why it required hours for this to happen. Reaction is very slow, just because this adhesive is too thick. So that's a hypothesis. We actually did an experiment. The way we did experiment is we control the thickness of adhesive by using a nylon mesh. So we can buy nylon mesh of different thickness. So 50 micron, 100 micron, 200 micron, and then measure adhesion energy as a function of time. So you can see for thinner adhesive, the same adhesive, you just reach a steady state faster, no problem. And furthermore, the time to adhesion really scale with the thickness by this diffusion time scale. The scale with a thickness h squared. There's no problem. There's no mystery. It's a diffusion of little ions that cause you problem. Once you know that, of course, you have all kinds of way to do this. So far I've explained mostly to you about wet adhesion. So I need to go fast. I'm running out of time. I also need to tell you this adhesion is stretchable. So adhesion stretchable, it means if you did adhesion after stretch, do you still have a high adhesion energy? This kind of experiment was never done before, right? It's not a requirement. Who want adhesion to be stretchable? We want, because we want to adhere tissues and hydrogels. After adhesion, tissue need to be stretchable. Heart still need to vibrate. Okay, so we test this with our thing. So after in-plane stretch, for different amount of stretch, up to 8 times of stretch, enormous stretch, adhesion energy hardly change. You can see that. And also we do cycle. After 10,000 cycle adhesion, just stretch back forward, adhesion energy hardly change. It's a very stretchable adhesion, not a problem. Now itself is very interesting. I will not have time to show you all the experimental evidence. We publish papers. So the essential idea is for this chitosan. Chitosan actually itself is a very brittle, like tofu. When it stretch, actually it is stretched into pieces. However, polyacrylamide, this stretchable gel, hold it together. So even though you stretch into pieces, the adhesion still remain intact. So we have evidence. I'll skip these evidence. And we call this thing molecular staples. So the idea is this is a macroscopic demo. I have students made 2 pieces of rubber, just regular rubber, and use a staple, for binding books, right? Staples, steel staples. So because this material itself is stretchable, even with the steel, you can still stretch this, no problem, right? So it's just like this. So you form islands, and these islands cause binding. The island itself can be stiff, but the whole adhesion surface can be stretched, no problem. So this is another strategy. I don't have more time. Let me just quickly reach the end. But I do want to tell you this idea. The idea is triggered detachable adhesion. Let me just tell you idea without telling you experimental evidence. The paper is published last year. So the idea is the following. For many applications, let's say you want to glue something to people's hand to do drug delivery, but afterwards you want to peel this off easily. Adhesion strongly, but peel off easily. So it's a trigger detachable. So we made one version. So you have a strong adhesion from a topological adhesion. And then when you want to detach, you shine a light. And there is a photoresponsive functional group. You shine a light, it opens, of course it's attached. It works very well. I don't have time to show you. It's a familiar chemistry for people who know chemistry. It's iron 3, iron 2 chemistry. Can allow you to do that. I don't show this video anymore. No video. Let's reach the end. So I will not have time to talk about this. I will, I will reach the end. Have a few summary slides. In this talk, I mainly talk about topological adhesion, black network connect through a red network. But there are so many different topologies to making connection. The message of this page, this is published, is to show when you design your adhesive, you really need to explicitly design your topology, not just select a bond. You need to design your connection. So in particular, for example, you can do a topological connection between red and black without a third network. It's also possible, right? Or you can use a polymer chain. I just demonstrate this with a pig, right? And of course, you can do direct bonding. There are also other topologies. You can create hundreds, thousands topologies. The point is not making exhaustive list. The point is you need to think about this. This is a new design principle you need to think. So we actually have demos for many of them also published. You can also satisfy additional requirement. You want to have a degradation. This is a recent work. I don't have time to describe. This is really, it's a new technology or new product or beginning of luminescent fabric. Each fiber is stretchable and luminescent. You apply a voltage to the fiber and the fiber shine light. And it's stretchable. That requires multi-layer of dip coating. Elastomer on hydrogel, hydrogel on elastomer, and there's ceramic particles. When you make devices, all these interfacial adhesion become crucial. That knowledge is largely missing, waiting to be created because of wet adhesion was not successful technology even 5 years ago or 2 years ago. So it's widely open. Now here we tried a little bit 3D printing, print a hydrogel elastomer net, structure. Now here's a demo I really want to show. We need to make artificial axon. Second time, after all these improvements of materials. So this is our artificial axon, hydrogel, and so it's so well made. It can sustain abuse of a hammer, real hammer, not artificial hammer. Artificial axon needs real hammer function. All right, so let me summarize this. Apologize, I am a few minutes over. So the summary is very simple. I believe there is enormous scope. We just touched this superficially about inventing new ways to do adhesion to maintain wetness and elasticity. Just a new requirement of our humanity, right? And to do that, we have the traditional tools, chemistry and mechanics. And this new thought, it's not terribly surprising. You need to have a topology, making good connection. And of course, nature is full of holes because we are made of polymers, people, waiting to be stitched. So, and we have long tweets about this kind of thing called 100 years of toughness. This year is 100 years of fracture mechanics. So we talk about these things every day on Twitter. Thank you very much. I apologize to go over.
Thank you, Zhigang. Very interesting talk. Now we're open for questions. I believe, Johan, you started to ask questions. Even during your talk, many people ask questions and provide answers on the chat box. But Johan.
Zhigang.
Yes.
How are you?
So
morning.
happy to see you.
Same here. I enjoyed it.
Thank you.
Lots of new chemistries at the interface, but the concept of wet adhesion is not new to people like Herb Wade at UCSB.
Correct.
Right. So they understood how marine animals can stick to rocks. In fact, once they stick, they cannot even detach their legs. They cut them. To move around, they cut them.
Mm-hmm.
So I think the wet adhesion concept is understood, well understood. You are just providing new chemistries, new approaches for applications. Am I correct?
Or of course, wet adhesion in terms of a practice is as old as humanity, right?
Yes.
So some animals learn even probably before us. If you, or we are aware, of course, aware of this what is this muscle inspired adhesion. Or several things. We actually studied their papers. Several ideas are very vague in their design. They tend to emphasize bonding. They have a very vague understanding of dissipation. So if you look at their number, their adhesion energy actually is low. Often they do not even measure it. If you do not measure, you don't know how bad you are. They're actually bad.
Actually, Paul Hansma did some measurements with the atomic force microscope as well.
Yeah.
So
all these numbers.
I agree that I think they understood the concept of wet adhesion.
Yeah.
But being marine biologists, they did not understand the mechanics well enough.
Yeah. So the dissipation is the one thing they missed.
Yes.
The other thing they missed is topology.
Yeah.
Of course, if you talk to chemists or polymer chemists, they do topological entanglement all the time. It doesn't surprise them. But seeing this so many varieties you can do, ingenuity. I skipped too many. Some of my students will be incredibly upset with me. They spend years to do this. I select one page or two. I eventually had to skip that.
Well, you have to give another seminar.
Yeah, I really apologize to people. Jason, I see you here. You laugh at me. Right. So,
thank you, Zhigang.
Yeah, thank you.
Okay, Tahir Saif.
Zhigang, fantastic.
Thank you.
I always learn from you. Couple of questions. One is basic and one is more practical.
Yeah.
The basic one, maybe it's trivial, but it's not clear to me, is what is the role of van der Waals forces? You talked about monolayer kind of thicknesses and the two layers are coming very close. That's one. And the practical part is, where do you see the scaling effect? I'm thinking in terms of, when neurons get damaged and the signals cannot be transmitted, halfway through the signal is gone towards muscle, for example. Can this be a replacement of the injured neuron in the future? I mean, that'll be a transformative.
Yeah, okay. So I cannot answer the neuron question with confidence.
But the size scale may be a relevant one.
Yeah, I cannot answer a question. So, but you know me, my answer is also yes, we can. But you know how shallow that answer is. So okay. However, you ask a very specific physical chemical question about the role of all these physical non-covalent bonding.
Correct, van der Waals particularly.
Yeah, van der Waals in particular. Now, van der Waals in particular is not very good for us for the following reason. Because water doesn't do that. Water is doing hydrogen bond. And the strength of a hydrogen bond, we already know, you experience daily by touching water. It's not very strong yet, right? So the reason van der Waals force is not good enough for us is just we have too much water. You really need to bond polymers directly. Polymers, if you still use van der Waals interaction and you're a minority, that become hard. So if your polymer is already few, you need to have this field really count.
Mm-hmm.
Many delegates if you only have few states, right? So that kind of idea.
Mm-hmm.
Yeah, you need to have a strong bond.
Mm-hmm.
Yeah. But we did have we did try to use a kind of a strong non-covalent. Some non-covalent bonds can be strong. For example, our chitosan has this hydrogen bond. And especially if you do hydrogen bond, several hydrogen bonds in a row form a complex, 5, 10.
Mm-hmm.
That bond actually is almost as strong as a covalent bond.
Mm-hmm.
This we know by testing our numbers. So I showed you some numbers, almost as strong.
Mm-hmm. Mm-hmm. Now, going back to the size scale question, it looks from the theory and the hypothesis that you presented, it should be scale independent, right? I mean, it has to be many, many molecules involved, but it doesn't seem to be dependent on micro scale.
Yeah. So the fundamental topological adhesion only engage one mesh size. I think we have enough data to point to substantiate. I wouldn't say this is a firm hypothesis yet. More tests need to be have, but it's in the right direction. So if assume that hypothesis is correct, only one mesh size, you're right. Size scale become irrelevant. You're just going mesh size. However, you and I know if you engage any bulk dissipation, that bulk dissipation is size dependent. Yeah.
Thanks, Zhigang.
Yeah, thank you.
Good. Nanshu?
Thanks, Jimmy. Hello, Zhigang. Wonderful talk. Always enjoy all the knowledge as well as the jokes. So my question is for the topo adhesion mechanism. What if the other surface is tissue, which is not a polymer that can allow us to form those kind of stitches? And also, what if it's like a polymer which cannot accept diffusion of chains or hydrogen bonds?
Yeah. So we have tested that many tissues can actually form topological adhesion. So it depends on type of tissue, also preparation. But you're quite right. Certain tissues, for example, skin, especially when skin is not well treated, it's hard to form topological adhesion. In this case, then you have to rely on other things. For example, these we call it each ways to make connection. We call it a topology. So making direct bond is an option. It's actively pursued. So I actually have a few slides to want to say the scope of making wet elastic adhesion is enormous. Many of these opportunities involve things other than topological adhesion, other topology. That's true. Even for our hammer experiment, that elastomer hydrogel adhesion is not top adhesion. It's just direct bonding.
So for some tissues, you say it is possible.
Yeah, many.
How because of the protein chains?
Yeah, because the tissue itself is hydrogel, right? Many tissues are hydrogel.
But there are cells everywhere.
Yeah, sure.
So you are making the stitches between cells, like.
I think in our demo, probably mostly actual cellular matrix.
Okay.
Making the adhesion. Yeah.
I see.
We didn't study, you know us, right? So many are our tissue example. Samples came from grocery store. Not very serious for mechanical engineers.
Thank you.
So yeah, other people need to really kick in to do this kind of thing.
Okay. Jerry?
Jiahui is here. Jiahui is an inventor of top adhesion. Jiahui, say hello.
Hi, everybody.
Yeah, he is now postdoc at Langer and Anderson Group, pretending to be bioengineer.
No, I'm still a mechanical engineer. Just broaden my vision right now.
All right, all right.
Good, good. Gerald?
Hi, Professor Suo. Thank you so much for the talk. I've been certainly a big fan of the 100 Years of Toughness thread on Twitter and learned a lot from that. And I certainly learned quite a bit more from your talk this morning. So thank you so much for that. I've got some questions that are a little bit in the soft matter hydrodynamics domain related to some of the stuff you're talking about near the end of the talk.
Yeah.
The first one is, so I thought that was a really cool physical picture that you painted of how the polymer diffusional timescale is not really what sets, that's not really the limiting thing, it's the reaction timescale. So it's the diffusional timescale for the ions across those macroscopic or maybe mesoscopic gaps.
Yeah.
So my question is, do you envision any techniques, perhaps some sort of field assisted diffusion or creating some highways or some pipelines that can enable fast diffusion across those gaps that could help cut that time scale? Because that's a several orders of magnitude opportunity to get stuff faster.
Yeah. Thank you. Thank you. Incidentally, that cool picture you loved was created by Jason. Jason, say hello to people. Jason, say a few words about yourself.
Hi, everybody. So that was a recent paper by myself and Jiawei and others painting this picture. And I'm currently a PhD student with Zhigang at Harvard.
So Gerald, thank you for raising that question. I thought I was too fast, but I guess I was not fast enough for you. I really enjoy your comedy show on YouTube. It's a fantastic. All right. Anyway, so this is Jared is a assistant professor at CMU, right? CMU, mechanical engineer.
Civil and environmental engineering, actually.
All right. Okay. All right. Good. Migrated. Anyway. Yeah. So the question is, can we rapidly, vastly enhance reaction time? The answer, of course, is yes, we can, right? It becomes generic answer, yes, we can. But this time I have some depth. So this is just a pH-triggered top adhesion. So require on pH diffusion from the substrate through the layer. But if you design your top adhesive with all the ingredients already in the layer, then diffusion is not an issue, right? It's possible. So we have a separate, Jason had a separate paper and Jiawei about just have everything has in one pot, then just reaction time. There's no diffusion per se, just reaction. You just need to accelerate that reaction. Then, of course, the chemists have a zillions way of accelerating reaction. One thing is called enzyme. So that's not our, by that time, it's not our game. Our game is to have a schematic.
That makes a lot of sense. Thank you. And one more quick question on there, just because I'm not really familiar with this world of materials. So I'm curious, in thinking about these diffusional timescales, constructing them through a Stokes-Einstein type approach, some KT over 6 pi eta times the length scale. What's the range of viscosities that you see in these materials?
Oh, for ions is about any ion, 10 to minus 9 meter per second, single ion. If a long chain, depend on chain length, we use a number 10 to minus 12.
Okay.
The thing is, even with a lower, such a low level diffusivity, if your diffusion distance is just one mesh size, it took a millisecond. Right. So diffusion of polymer is never an issue. The key insight is to have a secure top adhesion. You only need to engage one mesh. Yeah, that's a brilliant hypothesis. So, Jason, thank you.
I maybe want to extend on that by saying that we have an example, cyanoacrylate, this is a very fast reaction. You look at in this paper, we compared, say, the rate constant of the chemical reaction, and cyanoacrylate is very fast and has a very high concentration. So this reaction happens in like a second. And you can have very tough top adhesion using cyanoacrylate. It's just a matter of designing the chemistry of a top adhesive to match the application. Because in some applications, you actually don't want it to be as fast as cyanoacrylate. It's case dependent.
Thank you, Jason.
Thank you very much.
So the cyanoacrylate story was discovered by Bao Hong. Is Bao Hong here? Bao Hong is not here. Another student, a graduate student, who also did this artificial axon stretch. So in that video, there are white hands and the black hands. They work together. Black hands belong to Bao Hong.
Okay, Tian Tang. By the way, introduce yourself when you start the question.
Yes, thank you. So Zhigang, this is Tian from University of Alberta in Canada. Very nice to hear you talk again. Always very rich and fun to listen to. So I have a couple questions. The first is the adhesion energy that you presented. I assume that's under quasi-static loading condition that you are reporting those values. I wonder if you have looked at the rate dependence of the toughness, because you've also mentioned some rate limiting process in those materials. So I'm wondering about the rate dependence. Yeah. Another question I have is, have you because it's wet adhesion, and have you tested those materials actually in a aqueous or some kind of wet environment? And it's particularly interesting to me that this pH dependence of chitosan. So I imagine if your environment is actually a solution and you can control the pH of that solution, then you might observe different adhesion.
Yeah.
Thank you.
Thank you, Tian. Really good to see you. Thank you. So now you remember we also presented some velocity energy release VG curves. So you can see as velocity goes low, the toughness goes lower. There's actually a threshold. So it is rate sensitive. PO tests allow you to do that just by peeling at a different velocity and measure the force. That's how we do it. Now for humidity, some experiments you need to preserve humidity. It depends on the sample size. If your sample is really big, you can actually do it in air if time is short. And we tried, it doesn't matter too much. But if your sample is thin, you need to have a humid environment or even test underwater. Indeed, the result is pH sensitive if you control. Yeah, all these are the variables.
Okay, thank you. So you have actually beautiful ways of controlling the adhesion at pretty much any level you want if you can control the conditions properly. That's really beautiful.
Yeah, thank you.
Trisha, you're next.
Good morning, Dr. Suo. Very nice talk. I learned a lot. So I have a question related to the reaction diffusion timescale.
Yeah.
So the timescale that you are mentioning for the reaction, isn't it also like similar to a diffusion timescale itself? Because there it's ionic diffusion to the macro scale thickness.
Yeah.
Right?
Yeah.
And basically, can't it be interpreted at the same way, like if there is not enough ion to initiate the reaction won't happen, but once the reaction initiates, it's pretty much instantaneous?
Yeah, that's for that system, correct. But we also have a system that the reactants, all the reactants are in the gel itself. For example, if you do EDC chemistry, Jason, where is Jason, right? Jason has a system where you just do this peptide bonds, forming this bond with NH2 and COOH. Forming that bond require EDC, this enzyme. And you can tune the reaction rate by the concentration of enzyme. So he showed that, yeah, you can shorten the reaction time.
Thank you.
Thank you.
Bingbing Ying.
Hi, Prof. Suo. Nice talk, very nice talk. First, introduce myself. I'm a PhD student from McGill and currently doing my exchange at the University of Toronto. One of my supervisor is Professor Jianyu Li.
Yes.
Okay, so following is my question. Actually, this very basic question relates to wearable electronics. And as we know, hydrogel is known for its good biocompatibility. And some ionic hydrogel rely on salt or even in high concentration to achieve the good conductivity, right?
Yeah.
So for wearable and even implantable use, can we still claim ionic hydrogel achieve the good biocompatibility or low biotoxicity due to the high concentration? Because some people use ionic hydrogel for the implantable use. Yeah, that's my question.
Thank you. Thank you very much. Also say hello to Jianyu. Jianyu Li, the person who did this pig experiment. He couldn't be here. He sent me an email. He is teaching at the same time. Anyway, so about hydrogel of high concentration of ions. Of course, it's not biocompatible. Because if you allow this ion to be directly in contact with human body, ions will leak out. You cannot even maintain that. So then a couple of solutions, people explore that. So it means you need to have a good insulation. Yeah, you have a good insulated elastomer. We test some elastomer. The existing elastomer we tested, we published a paper too. Not very good. They leak, especially at a small scale. It's too thin, leak ions. But Jiawi, my colleague Jiawi here, not Jiawi, Liu Jia Liu, assistant professor here, he really is a genuine bioengineer. Told me he might have found something that is considerably better as an insulation. But in general, I think ultimate solution, we should mimic human body. If a human body, the natural axon can function with a low concentration of ions, we should do that too.
Okay. Thank you.
Thank you.
Thank you very much.
I think it's my turn.
Yes, Koji. Yes.
Hi, Jimmy. Hello, Zhigang. Good morning. Good morning from Purdue Mechanical Engineering here. I'm KG Zhao. I was a student of Zhigang Suo. My questions are kind of following with Nanshu and Tahir's question. So following Nanshu's question, so in many cases that there's not much choice for the substrate material. For example, in many devices we have soft material on hard substrate, let's say. And many times we use ITO, for example, use a current collector, but it's very hard to engineer the interface between the soft material with the substrate, this hard substrate. So as already discussed earlier, that there's a lot of chemistry we can use for soft material, but it seems not many choices for soft hard material. So maybe can you like enlighten me that, or if you have any advice that for such systems, how can we engineer such a systems, particularly from a mechanics perspective? So this is the first. And second, following Tahir's question is about the size effect. This is another practical limitation that very often the film is very thin, and sometimes it's just a few hundred nanometer, at most up to a couple hundred micrometer, which is a very thin, much thinner than hydrogel. So perhaps it's a kind of little more difficult to answer this size effect, but maybe my more practical question is, for such a thin film, how can we do experiments to measure the adhesion strength for if the film is really thin? Thank you.
Thank you. So the first question is about a soft material on hard material. So this actually, believe it or not, it's an old question, has a couple of known solutions. So the context was the following. One concept we're very familiar, we published one paper, is writing a couple more. It's called a hydrophilic coating. You're one of the group member. So there was an old group member, Xiaoyan, Gong Xiaoyan has a company, right? His company is produce medical instrument for guide wires to do microsurgery, minimum invasion surgery, right? These guide wires are made of metals. They need to be coated with a hydrogel called hydrophilic coating. This has been done for decades, so it's known. So there are two broad strategies people use. It's not very explicit in textbooks or papers, but we look at their patents. Two broad strategies. Strategy one, you just create functional groups on the surface of a hard material, such as a silane. And then once you have silane functional group, you can grow hydrogel with covalent bonding. So this is one. This is one we adopted. The other is not even have a name. We call it a jacket. So what you do is you have a metal, and then you have a plastic coating, wear a plastic jacket on the entire metal. Now you have a plastic, and then grow soft gel on top of this jacket. So many commercial products is based on jacket.
Very good.
So that's one. Hard and soft. Oh, you say how thin structure be tested adhesion. This problem, so the world greatest authority here, there are two. One died, Chin Ma, in the context of microelectronics, so nanoscale layers. And the other guy is alive, Professor Rainer Dausgaard at Stanford. He's still doing this. So the idea is that if you have a thin layer on a substrate, all you need to do is put another layer on top in some way, and then do peeling test. Yeah, they actually did nanoscale films.
Okay, yes, that's what they're trying to do, but still it's quite a challenge to do.
It's a challenge. It really is a challenge, but they have made it into an art. But the art they developed really were for hard materials. For soft materials, so far, we just try to do it one way or another using peeling. Essential difficulty is how do you put the backing layer on without affecting the thin layer.
Okay.
You just need to be creative.
Yeah.
I think this is a very important question to ask, and it eventually will be a very important technology.
Thank you very much. I also have a naive question, if you allow me to ask. So for the earlier part, you showed the Inotronics and this amplifier, very fancy. I was kind of outside of this field, but I want to ask, is this something very similar to transistor? Anything different from that? There seems a lot of choices already in the field. Why we do this soft Inotronics?
Yeah. So in terms of functions, they try to mimic human, animal. They also try to mimic electronics. So the function, there's actually Ionic transistor. We recently published a paper led by our leader, Ryan Haywood, a science paper. Is Johan still there? Johan used to be Ryan's advisor. Anyway, okay. Now, so you ask why do we do Inotronics? Because it's because of the following. Because us. we are ionics, right? Ke Zhizhao will never become an electronic person, right? It doesn't matter how fast you evolve. So you're ionics. Right. And we also know electronics becomes so good for data processing, and you need to make that connection. That connection is Inotronics. Okay. It's just that interface, whatever you do, eventually you need to make ions talk to electrons. That by definition is Inotronics.
Okay, thank you very much.
Yeah. Okay, Matteo.
Okay. Hi, Zhigang.
Hey, Matthew.
Yeah, it was so nice to hear you speaking about so many interesting subjects as usual.
Thank you. To see you again after all these years.
Yeah, we're starting to miss to meet each other.
Yeah.
Yeah, anyway, this is so Matteo Ciccotti from ESPCI in Paris. And I have a couple of questions. The first one is, in general, adhesion is very affected by sliding condition locally, potentially. So I wanted to think if you have thought about any link in this works between sliding and debonding somehow. And then I have just a sub question, because I recently started to work with some pork gelatin in some experiments. And indeed, I was expecting it not to stick and not to slide, not to stick and to slide easily. But I was surprised it was sticking everywhere. I could barely unmold it from molds. And then also I expected to slide, and it's very difficult to make it slide either. So you know why does it stick so much, even without all topological stuff?
Oh, yeah. Once you try to measure them, we try to measure these things without covalent bonding. So I guess give you an impression it stick quite well because it's so soft, so stretchy. The adhesion energy without covalent bond typically is on the order of 10 joule per meter squared. We have measured, other people have measured. Your colleague Labler have measured. It gives you an impression it's quite sticky, but the adhesion energy actually is low, 10 joule per meter squared. Now, having said that, that 10 joule per meter squared can achieve a lot of applications. For example, all our first generation devices are demonstrated with that kind of adhesion. It's fine. It's fine. It can survive. So sliding, we don't see a lot of sliding. Yeah, we don't see a lot of sliding. Do you see sliding?
Yeah, I mean, generally, that if you put just an hydrogel over another hydrogel, then you see sliding very easily because it's almost water on water.
Yeah.
Or even if you put like an adhesive, which is rubbery on another rubbery stuff, so the two are mobile, then they can slide, and not completely, but there is some sliding. Yeah. And indeed, this really couples a lot with the bonding.
Yeah,
that was shown by Chowdhury some years ago. So I was wondering, if you took this into consideration somewhere. But of course, if you make grafting or topological bonds, then you're not sliding. Yeah.
We did work a little bit, publish a short paper also on, I think it's the extreme mechanics letters, about how to enhance friction. Or enhance, lower the friction, essentially by having so you already point out, if you have a lot of water on the surface, then the friction will be very low because you're essentially sliding on water, right? So the question is, how do you maintain a layer of water on the surface? Right? So one strategy we took was a strategy we learned from a joint, a human joint. There are molecules, synovial fluid. So what we did is put some polymers in, mobile polymers in our gel. And these mobile polymers can migrate to the surface. When these mobile polymer to the surface, they are hydrophilic. attract a lot of water, put a lot of water on the surface. That reduces the friction. That is very slippery.
No, that's interesting, because I need my gels to slide indeed over some glassy polymers.
Yeah.
Now the solution I have is that I put water, and then, but it doesn't it's not stable. Yeah.
But once we put a mobile polymers in, that's very stable. We can slide.
So what kind of polymer? Just tell me the name again.
Oh, we put alginate, just a highly hydrophilic. I'll send you that paper.
Okay, that's very good.
Yeah.
Okay, thanks a lot, Zhigang.
Thank you.
Wonderful, wonderful. Thank you. Su Lin, next.
Hi, Zhigang.
Yeah.
Wonderful. So I have a very practical question to ask.
Yeah.
And that's always in my mind. I never get a chance to ask.
Yeah.
So when you deliver lectures, presentations, right, the scientific contents are broad, very deep, no doubt about that. But I found that when you deliver presentations, it's also very entertaining and transparent, very easy to understand. I may ask my daughter, this high school student, to watch today's your talk. So a lot of people in academia are struggling delivering lectures. Oh, by the way, there's no equations in your lecture, I found. Right?
Well, we have 4 equations. 2 of them belong to Jason.
Minimal equations in your lectures. So a lot of people in academia community are struggling delivering smooth lectures or presentation, including myself. So what's the secret behind your lecture? What's your philosophy? What's your principle? I think that 10 delivering very nice lectures can learn from you. So I think everybody in this community want to learn from you. What's the principle behind how you prepare your presentation? You put a lot. So when I listen to your presentation, I put a lot of pressure on myself.
Yeah. Su Lin, okay, Su Lin is one of our editors. He will give the webinar next week.
That's why I say a lot of pressure.
All right. So
Zhigang, write a paper. We'll publish in Extreme Mechanics Letters.
So when I was young, K.S. Kim pointed out to me I should study Feynman. So I collected many of his books, and also now today there are many of his videos online. You just watch him. He talks about things even harder than what I talk about, right? Quantum electronics. I never understand that. But if he talks about it, you feel you understand it. So he said it's very simple. This is what he said. He said, just figure out what you want to tell people and tell it. So perhaps people, when they use a very intricate experimental data and very intricate equations, they are still in the middle of their thought. They're not sure what they want to tell people.
Interesting. Yeah. Jing Du.
I think it's me, right? So
No, next is you.
okay. Hello, everybody. So this is Jing. I am an assistant professor, also from Penn State University, same as Professor Su Zhang. Yeah. And then Professor So. Besides the compliment on your presentation skill, I want to ask you something like a technical question.
Yeah.
So your talk is fantastic. The very strong adhesion is so wonderful. It reminds me of the adhesion in the hard materials. So in the metallic implant, people used to introduce hydroxyapatite coating to increase the adhesion between the between the metallic implant and bone. And then it turns out the adhesion is too strong, so that it creates some problem. So I want to ask you a question. That in your study, have you ever thought about tuning the adhesion energy, make it instead of 20 and 1000, how about the other values in the middle to make it tunable? And also, a related question is that once you apply the adhesion, once you make it stick to some surfaces, for example, the tissues, have you think about how to remove them? If in an application there's a need to remove them, is it possible to make it removable? Right.
Thank you. Thank you. So tunable adhesion, yes, we can tune. Yes, once you have all these variables, for example, I showed that the pH can clearly tune. But of course, pH, for many applications, you probably don't want to change pH too much if it's inside body. But you can have all other molecules. Yeah, tuning should not be too hard. Of course, depend on application. Maybe you have so many constraints. I don't know the application you mentioned sounds very interesting. Now you also ask about removable. I was too fast. I don't know. Gao Yang is here. Gao Yang is a lady. Recently gave birth to a child. She's just brilliant. She created this photo detachable adhesion. She also had many other versions of thermal detachable. The key idea is if you put in functional group, which is responsive to light or heat, you can easily remove adhesion, for example, by shining the light. So I went through too quickly. I actually had a few slides about her work, just beautiful. It's published in Advanced Materials in 2019. I think many things can be done with trigger removable adhesion, and also many applications as well. We just scratch surfaces. Yeah, the lead author is Gao Yang. Yang Gao. Gao, last name is Gao. I don't know if she's here. It's late for her. She's in China, giving birth to a child.
Okay, Li Qing.
Thanks a lot. Thanks a lot for that. I'm gonna follow the paper.
Yeah.
Thank you. Sorry, I made mistake just now. Yeah. Thank you, Professor Jamie and the Professor. This talk is so fantastic. I really enjoyed it. Thank you very much. Here, I just have 2 questions about the test, the pure test that you did. You showed in your slides. So first one, in the pure test, you showed the relationship between the force, applying force, and the time. So I found the curve is smoothly going up, then going to constant.
Mm-hmm.
So I just wondering, did you find the kind of time softening before you go into the constant?
Mm-hmm.
Yeah, this is first question. The second question is about the crack propagation during your pure test. Mm-hmm. So if you look at the crack front during the peeling test, did you see that it's cracking, it's constantly or kind of jumping or an additional cracking or something different pattern? So I just would like to know these 2 points. That's super cool. Thank you very much.
Okay, Li-Chun, really nice to see you. So yeah, about pure test, I only showed a schematic, right? Just try to not confuse people. Oh, that curve is very rich. Often we see a peak and go down. Peak probably associated with nucleation of a growth. Remember, initially, the crack is prepared by some blunt instrument. So the crack, blunt, just refuse to grow. You have a higher and higher force. And once it grows, the force really softens. That's common very often. When that happens, because the pure tests were done by many people, what we commonly do, people collectively do, is just ignore that peak, look for steady state. So your second question is even more interesting. So the crack often grow by stick slip.
That's a good call. Yeah, thank you very much.
Yeah, and people study this. So far we haven't seen a good study on stick slip of a hydrogel. In hydrogel, it's so pervasive, almost make us believe there might be a separate mechanism of stick slip just for hydrogel, such as due to polar elasticity. We don't know. But a stick slip is often even for testing elastomer.
Great. Yeah.
Very good. Vital? Vito?
Yeah, hello, it's Vito, yes.
Vito.
Thanks, Zhigang. It's Vito from EPFL. Fantastic talk. I have a quick question about bulk dissipation to enhance adhesion and how this relates to mechanical properties.
Yeah.
Like from what I understood is that you need some viscous dissipation to use to enhance the toughness of the adhesion. I was wondering, how does this relate to like having a stretchable material rather than a stiff one? Can we still have bulk dissipation also with stiff materials, rigid materials, or does it have to be stretchable? Does it help to have a stretchable material to have higher bulk dissipation?
Yeah, thank you. So of course, bulk dissipation was first studied by now it's 60, 70 years ago by Irwin and Orwan in steel. So it's a hard material. There it's just plasticity. In soft material, bulk adhesion comes from non-covalent bonds, or even covalent bonds somehow can snap before the sample fail. There are a number of ways to design this. The key person or lead person in doing that is Jianping Gong. She will give a talk webinar in December. She is a spectacular queen of a dissipation. Yeah, but to answer your question, for hard material, yes, metal plasticity or plastic plasticity, these are all dissipation mechanisms.
And there is no clear relation between having a soft or hard material. It works in both cases equally, right? It just depends on how it can dissipate energy.
Right, yeah. It's not specific to soft material.
Okay, Yuan?
Okay, can you hear me?
Yes.
Okay, so I'm Yong from Max Planck Society. Actually, I also spent 10 years at Xi'an Jiaotong University.
Great.
Okay, so we are now working on engineering hard muscle for failing heart regeneration. So I think your tough adhesive gel can be used for the implantation of the engineering hard muscle. I have a short question. Maybe you have already talked about it. So is this gel degradable?
So we have a degradable version. We just learned from other people. Yeah, you can make it degradable.
Okay, yeah, because we hope that later, after the implantation, the heart will merge the engineered muscle.
Yeah.
Okay, yeah, thanks.
Yeah, thank you.
Okay, who's after you? I think France Bobby.
Hi, Zhigang. I like that chart that you put up with, what was it, 20 entries of types of bonding? And so I was thinking of a very simple case that we know from practical experience. If you build things with PMMA, with plexiglass, you just paint on some methylene chloride and stick together. And I think of that just as a solvent. I mean, it just softens the stuff up and you put it together. So what sort of a bond would you get? Because I don't think that rearranges the topology of the PMMA change, right? So how does that fit in your scheme of 20 mechanisms?
Yeah, 20. First of all, Franz was my teacher. He taught me material science when I was a real applied mathematician 30, 40 years ago. So what I said are wrong, of course, it's a Franz problem. All right. So for plastics, especially thermoplastics, there is a traditional mechanism invoking interdiffusion. I don't know that particular thing. you're doing, whether this is doing this or not. But so it's a thermoplastic. If you warm this up, it becomes mobile. Then chains coming together, and then you lower down the temperature. They're entangled chain. These are physically entangled, not topologically entangled, meaning you can separate them, but it's a thermoplastic. They're as strong as other part of thermoplastic. I think maybe solvent is doing the following.
Yeah.
It's loosen the chain a little bit, and you put together, the solvent evaporate, and you just become plastic again.
But I would still call that topological. If it's not just van der Waals, right? So you have to hook them together somehow. I would still call that a topological link if the chains. Otherwise, I couldn't imagine that it would be as strong as it comes out.
Yeah, but it is a pull out against the friction of between chains. You do not need to break atomic bond anymore.
Yeah. Okay. Yeah. But again, that friction is probably affected by the topology, I imagine.
Yes. Yes. So in our language, is one kind of topology, but it's not within the. So at one point, this chart was designed by Jiawei is here. It's in Jiawei's review article. We try to be complete. At the end, we admit defeats. Just number of possible, combination, just enormous. And you can always imagine why people may want to do a particular thing. At the end, we said, okay, we just give some representative examples. Maybe you see these 20, you can get inspired. Always remind to ask yourself, what is the topology?
Okay, thank you.
Yeah. Thank you.
Okay, Tang.
Thank you, Jimmy. Thank you, Zhigang, for another great talk, which epitomized two things. First is what is a great research topic? And the second is how to present a good research. My question, I actually have two questions. The first question is actually echoing what happened before your webinar starts. Actually, I highly recommend those of you who joined this webinar or watching this recording after 9:30 today. Before the official webinar, we have an informal interview always. That's where you find the great questions, great answers over there. So Jimmy asked a question at that part about your research ideas. For those of you who are familiar with your research, and you always do original research, Jimmy's question was, how did you get all those original research ideas? Your answer was, you have a long list of problems you are interested to work on. And I think you are too humble to really value how exciting or how valuable those problems are. My question actually is, I think out of my curiosity, but I think I'm not alone on this. How did you accumulate this list of problems, and where did you find your inspiration to get all these problems? This is my first question. Second question is, to me, many of your research actually can really strike a balance, a good balance between a problem that can have practical significance and also the problem that you can really follow your heart and do something you are excited about. How did you achieve this balance between these two?
So about how can people do many things? So when I was younger than you, I asked the same question to John Hutchinson. He gave me a very simple answer. John, Zhigang, you just need to work on this for long enough time, then you will do a lot of things. For me, specifically, how to accumulate a long list. Here's the thing I noticed when young people like Jason and Jiawei, you work with them during a project, right? So these people have an enormous number of ideas. Sometimes Jason doesn't want to hear this, especially Jason, right? Gets so many ideas get sidetracked. So one idea become 10 different ideas. Then he started to pursue 10 different ideas. Then you get nothing, right? Then I just said, stop. Perhaps you have a sheet. List your 9 ideas on the sheet and work on this one particular idea. You can finish a paper. So that's how you accumulate ideas, right? You just stimulate a lot of ideas, but don't have other ideas interfere what you're doing now. So then you can pursue many ideas over the time. That seemed to be important to me. So you get inspired in many ways, but the most inspiring time is when you're engaged in solving one problem. You get a lot of ideas by reading at that time, by talking to people. Don't lose these ideas, just write them down.
Yeah, I have 2 questions.
Second question is about a presentation or about what?
No, about how do you strike a balance between doing research that just simply follow your heart versus having a practical, a problem-driven research that have practical significance and impact.
Yeah, this I think the main thought I have is I actually thought about these things. George Whiteside's 2 questions, right? It's a killing questions. What's new? Who cares? For each project, if you try to honestly answer these questions, that's the beginning of making that balance. What's new? Means you have to be interesting. Who cares? It means have to be interesting to other people, meaning useful. Actually, believe it or not, if you insist on this question to students and to yourself, over the time, you get better to making balance. But also there's another balance. You just say, yeah, people give you many examples to say, oh, so-and-so did something, wasn't appreciated 30 years ago, but now it's become important. For example, Griffiths study fracture of glass. Why do we study fracture of glass? It's a terrible material as far as the fracture is concerned. But then later, after 30, 40 years, it became important, right? So there are examples like that, but it's very rare. All you need to do is allow yourself to do some random things without direct applications. But if you do many problems, maybe 9 problems that have direct application or sounds like useful, and one problem just out of blue, I guess you're okay, or some other proportion. It's okay, you still engage, being active, but still do follow your heart. This is also something I tell my students, you don't need to constantly work on your project, what you're paid for, or what you need to report to me. You can follow whatever you want to do, but not all the time. So Jason, I have to remind him, you need to work on this one problem, ignore these other 9 problems, not ignore, record them, work on them later.
Thank you very much.
Great. Zheng Jia.
Thank you, Professor Hsia, and thank you, Zhigang. So this is Zheng from Zhejiang University in China, and I'm one of Zhigang's academic grandsons. And Teng is here. Teng is the bridge between us. So I have 2 questions. The first question is about the adhesion. In many of your papers, your group used pH values to trigger the adhesion. So my question is that possible to use other stimulus to trigger the formation of adhesion? My second question is about the hydrogel ionotronics. So these devices usually consist of hydrogels containing salts, for example, sodium chloride. And gel like this, so they have 2 species of mobile ions, sodium and chloride. My question is that possible to make hydrogels with only one kind of mobile ions, something like your ionoelastomers?
Yeah. So about a trigger, you can have many triggers. I skipped one page. Page is summarized by Jason. He has one page to say what are the triggers. For example, pH is one trigger. Jason just mentioned this crazy glue. It's a well-known glue, right? The trigger was actually just water. Water was a trigger. So many trigger we tried. So Jason also tried another trigger, this EDC chemistry. It's not a pH, just EDC chemistry. So that table is in his recent paper. He wrote a sequence of paper, right now just 2, published. Topological adhesion 1 and 2. That table is in topological adhesion 1 and published in great journal called Extreme Mechanics Letters.
Great. Mawa.
Oh, sorry, sorry, I have 2 questions.
Oh, I'm sorry.
Oh, yeah.
Another question is about the...
Yeah, you have a question about electrolyte. Yes, you can. Yeah, this is a standard answer, but this time I have a depth.
Okay.
You just use polyelectrolyte. For example, just a PAA, polyacrylic acid, has a negative charge on the chain, COO negative, and then in the surrounding could be sodium ion. Yes, you can. Very ordinary gel.
Okay,
it's the gel used for diaper.
I see. Okay.
Yeah.
Thank you.
Mawa.
Yes, hello, Professor. So thanks so much for the inspiring talk. Actually, I have 2 questions. The first one, when you mentioned about the slow response, and that's reminded me about ionic conductive polymer. I always witnessed that there's always a trade-off between the mechanical performance and response time. And this is challenging in the field, how we can design electrochemical mechanical system. So I don't know what's the answer. Do you think the answer about modeling or design or the topology or chemics part? So how we can close this gap between the mechanical performance and response time? And the second question I think is very interesting about friction mechanics, which initiated earlier about the cracks. So do you have any thoughts how we can design a material that can prevent crack initiation, never damaged? And do you think if we have to design such material like that, do you think it comes from the smart topology design or the chemical part?
Yeah, all right. Hey, Mawar. So thank you for these questions. Now, so when you say your response time and mechanical property, can you give me an example? What you have in mind? So
yeah, for example, since 2 years ago, I have to use ionic conductive polymer to activate the cochlear implant for surgical application, and we wanted to achieve certain forces with a certain speed, and there's always the trade-off between the shape of the actuator. For example, we have witnessed that if we have a higher thickness, it could give higher forces due to the interaction between the electrons applied and and ions stored in the material. So we found there's a trade-off between the geometry. If the higher thickness, it would be higher force, but the response time is very, very slow. And if we have smaller thicknesses, it will produce smaller forces. I can give example of how much is this force, but the idea was for small forces, but the response time, how it produces much faster. So there's always this trade-off. You see what I mean? Trade-off between the forces and still we don't answer this question. Why there's this trade-off is happening? Is it because we don't understand how we can design them or model them, or maybe the topology? I think that's also interesting. How we can get inspiration to design the material in a certain topology. So that's, I don't know what's the answer. I don't have the answer for that. So I'm curious to know what your thought for that.
Yeah, I have no thought about that. Okay, so it's still vague in my head. What is your practical system? But in general, or when we design or try to make this talk, we didn't really talk about, for example, fatigue resistant material. Or I recently gave a talk on this kind of thing. So the point is, or with a polymer structure, especially if you allow yourself to use a different chain length, different functional group, also possibly even mixing with other material, mixing with glass, plastics, or elastomer with hydrogel. Because you have so many variables, then the property space just enormous. So yeah, we need to be specific. Maybe you and I need to have a separate discussion about a specific situation. Now, what's your second question?
The second question about the cracks. Do you think how we can design a hydrogel that maybe it resists the crack propagation or prevent damage happening? Do you think it's about how we design the topology in a certain way, smart structures, or maybe the material side, or combination both of them?
Yeah. That's a great question because I have a great answer. So today we don't talk about, I didn't get a chance to talk about this. It's actually old ideas in fraction mechanics or in material science. It's about a length scale. It is there's a certain length scale material can tolerate. So if you create a floor smaller than that length scale, the material just tolerates that. It doesn't affect any property.
Yeah.
So that length scale for glass, window glass, is 1 nanometer, essentially atomic dimension. For really tough steel, that's 1 centimeter. So normally you don't worry about the flaws in a tough steel for that reason. For hydrogel, we actually studied this question. What's the length? This flaw sensitivity length in hydrogel is 1 millimeter. So now you think about it. If your application involves feature size less than 1 millimeter, essentially your hydrogel doesn't have stress concentration.
Yeah, thanks a lot.
Yeah, and we also can design this length scale, make it even centimeter or longer, depending on, we have a way to, we wrote paper about this kind of thing.
That's interesting. Yeah, thanks a lot. Thank you. Yeah.
Thank you.
Okay. Who's next? Was it Amit?
Okay. Hello, Zhigang. Thanks, Jimmy. Good to see you and always fascinating talks. So thanks again. I would like to pick your brain on the issue of heterogeneity, and this might be related to the topo adhesion or not. You would tell me, but several people, including some in today's presentation, have looked into the effect of bulk heterogeneity or interfacial heterogeneity in enhancing toughness and maybe consequently enhancing the adhesion. And one mechanism that this is enabled through is stress heterogeneity, right? So your crack can get trapped and then has a burst propagation, or as you mentioned, stick slip and so on. So I was wondering that if one of the synergistic effects of this topological constraint that you add to your network is in the way it introduces a stress redistribution in the network and on the interface as well. So do you think these two issues are in play, or it's primarily a topological constraint that you add into your network?
Yeah. It's a very deep question. So I have an answer so deep, maybe I should say something superficial first.
Well, all your answers are deep and great.
Superficial. So we all know this. First of all, heterogeneity is crucial in most material design. For example, let's use one classical example, ceramic matrix composite. This is something I did with Tony Evans when I was young. I didn't know what I was doing, but he taught me this story. So the story is the following. People want to have a high temperature material for engine, right? Ceramic can sustain high temperature. However, ceramic is brittle, right? All ceramics are brittle. So then he said, he was not original about this, but this is a story he told me. You have a fiber, ceramic fiber, which is brittle, and a ceramic matrix, which is brittle. You put them together, that composite is tough. Why? Because you have a weak interface. Why weak interface help you? Because when crack coming to the weak interface, you cannot have stress concentration on the fiber anymore. The fiber over long distance carry high stress. So heterogeneity really helps you to do this. So I know you have published recently about, also in EML. I was your editor.
I love the journal, of course.
So about how to use the heterogeneity to enhance adhesion. I think it's a great idea. All you need to do is work with people like Nanshu who can implement this in an experimental setup to solve some problem. But heterogeneity inherently allow you to, you said redistribute stress. I would say just deconcentrating stress. You no longer have a crack cause high stress concentration anymore. That's the key mechanics. There's so many ways to do this. Ceramic material composite is one way. The other way is, of course, is a glass fiber reinforced polymer. Glass is the most brittle material, but that composite is very tough as metal. We trust it so much, we make it into airplane. Today's airplane is made with that material, right? Yeah. It's a
Thank you, Zhigang.
Yeah.
Okay, very good. Bin Bin has another question on behalf of a friend of his.
Yeah, hi, Prof. So nice to see you again. This question is from Zheng Ying, now a postdoc from in Max Planck with Metin City.
Yeah.
And because today he has some technical issue for his computer, so he want to ask me. He want to ask the question. So his question is, for the science paper, he was wondering when the dielectric film is oscillating, there should be some heating problem, right? Heating occurring during the interface, leading to the increase of temperature. So he's wondering how is the performance after long-term usage between about the dielectric film.
A great question. We actually wrote a paper. So any concerns we have or other people have, we just write a paper. I also published at EML.
Cool.
Cool. Yeah. Cool. What we did is following. It does heat up, and what we did is doing thermal imaging to watch the temperature heat up, and also you can also turn it into a device. So heat up typically happen as the electric field concentration. So at a concentration edge of the hydrogel, it heats up. And when it heats up, what even can happen is salt, the water evaporate, salt become what they call salting out. You form a circle of white salt, it's possible. Now, this is a field concentration is a problem, right? We also propose some device in the same paper. So if you, because there's a field concentration, the field there is particularly high, you can drive some high field events, such as this electroluminescence. Apply a high field, you call luminescence. So now my take is the following. Right now, none of these devices are used by anybody.
Yeah.
Right? Yeah. So it's very hard for anybody. I cannot motivate my own students to carefully study failure mechanisms. They say, I would rather publish an interesting paper for yet another thing rather than study a failure mechanism of something people don't know if they want to use it. So here's the situation. What you ask is very important. I don't have a good answer. And the reason not good answer is it's very hard to motivate students really focus on reliability itself, mainly because there's no genuine users. It's still early days.
So for the follow-up, so I'm wondering, can you just empower the interface of hydrogel and elastomer with tough adhesion to minimize the heating problems. I was wondering, is that possible? Because during heating, there are some bubbles occurring in the interface, which will impact the oscillation of the bilayer structure. So I was wondering if that's possible to give them a strong adhesion.
Yeah, strong adhesion. Yeah, and also bubble. We also published a paper about a bubble.
Okay. I should check that.
Yeah. It's actually, we don't have many Nature communication paper. That was a Nature communication paper. I showed to France. France was pleased with that demo. France, do you remember we did the following thing? So hydrogel, right, has 90% water. So if you heat hydrogel just by heating it to, let's say 100 degrees C, water need to evaporate. But if you are just water inside hydrogel, the way to evaporate is to create a bubble. If you have a bubble, you have really damaged that hydrogel. That's a very easy thing to demonstrate. As a matter of fact, people demonstrate all the time. When you deep fry a piece of food, right? Put food in oil, and you see all the bubble come out, and you damage this food. Of course, we don't call it damage. Ooh, this is deep fried with a lot of bubbles, delicious. But it's a damage to the material, right? So that happens. However, here's what we demonstrated. Very cool. If you have that piece of hydrogel, all you need to do is a coat with a good adhesion, coat a thin layer of elastomer. Then that material can be heated beyond 100 degrees C without forming any bubble.
Just like high pressure pot?
Exactly. So that,
okay, I see.
That effect. I think. Yeah. So, but a high pressure pot, you use a very high thick steel and you still feel dangerous. Here, we just use 100 micron thick elastomer. The mechanics is interesting. It's simple. Check that paper out. It really tells you about bubbles.
As I remember, Zhigang, isn't there also help in to prevent nucleation? That you can postpone the nucleation of the bubbles, even if you're superheated. Then.
Yeah. Essentially nucleation, because it's known that in soft materials you create a cavitation. Right. By pushing surrounding materials. If surrounding material has elasticity or surface energy or toughness, then it takes much higher pressure to just create that bubble. That's essentially what it is. Yeah.
Thank you.
Robin?
Hello, Zhigang. Good to see you. I'm a former student of you. So I can say a few words about presentation on behalf of many group members here. So Zhigang gave us very hard time, of course, all the time, but in particular on presentation. I think we all know that. I think also one time I remember we were talking in the office, he said, Robin, I'm sorry, I apologize, I give you a hard time, but I give myself hard time all the time. So I think that's kind of the spirit we always have in writing papers and giving presentations. So the question is, a few years ago when I went out and people say, oh, you're from Zhigang Suo's group, then you must be a theoretician. But nowadays I went out, sometimes they say, oh, you must be an experimentalist. So the question is, I'm in this transition between theory and experiment in your group a few years ago. So how do you strike the balance now between theory and experiment and the connection between them? And what was your thinking process when you were having this transition? Thank you.
Yeah, by the way, Robin, so many people know, he was a co-inventor of a topological adhesion and was a co-author in most Jiawei's paper. He and Jiawei just work wonders together. Yeah, I do not speculate the relationship between them. but they work wonders. Anyway, so that's Robin. Strike a balance between experiment and theory. You know, the difference to me wasn't too big in the following sense. I haven't been doing detailed calculation or running finite elements for many decades. I cannot do these things. After my PhD thesis, I decided just playing with a computer is just not my thing. Just too disconnected with reality. So I always want to connect with questions I can understand, and connect with the things I can do, or other people can do. So in the past, when we had our own lab, remember we always collaborate with other experimental groups. I always ask people what you can do, and then we just frame a hypothesis that we can test in some way. So it's always that way. So whether it's an experiment or calculation or theory, or I actually didn't make much difference to me. I never felt I had a transition. It's always this way. Even from when I was a graduate student, I had to talk to experimentalists to see how each piece come into the story. But thank you for that question. Yeah. Sorry for giving you so much hard time. You're doing well. Yeah, you remember hard time with a fond memory. I hope we can all remember yesterday with a fond memory in some way.
That was very fun. Thank you. I mean, sincerely, that was very fun.
Okay, Li Hua.
Hey, this is Li Huajing from UCLA. I'm also a former student of Zhigang. Yeah, I'm unfortunately the last pure theoretician coming out of Suo group. Yeah. Thanks, Robin, for asking that question. I think that's the question asked for me, because I'm now trying the transition to become experimentalist coming out of theory background. Okay, so my question, Zhigang, you mentioned a few key components. So first of all, you need a covalent bond, strong bond between the topology and the material. Then second of all, you need energy dissipation from the bulk material to reach high toughness. Then my question is the volume. It's not only right the energy dissipation, but also the volume of the material involved for the energy dissipation is the key. So do you have a way to tune the topology so that you can enlarge or tune the volume of the bulk dissipation?
Yeah, thank you. To tune the volume dissipation, you have many ways. You don't need to have a topology probably can do that too. But the easiest way to do is just lower the yield strength. So for metal, for example, right? We know that if you have a high strength steel, your plastic zone will be very small. But if you have a low strength steel, your plastic zone become enormous centimeters. For gel, it's the same. For gel, it's very easy to control strength. So having said that, I should not, there's a nuance here about dissipation through bulk. There's a dissipation mechanism. I don't know if you follow this. Ruobing was an initiator of this. Ruobing showed if you have this kind of material with our tough gel, right, bulk dissipation, it performs very badly with the fatigue. It's just like a metal. You have a very high toughness, but a very low fatigue resistance, because all this plasticity doesn't help you with fatigue resistance. So that kind of gel, I would say first generation tough gel, probably will have very limited applications. Think them as a very soft steel, very limited applications. More recently, we have developed a new family of materials we call elastic dissipators. Essentially, the material before crack growth is wholly elastic. It's just like a polymer chain, right? Polymer chain, before it ruptures, it's elastic. But when this chain breaks, the entire chain energy needs to be dissipated. And that mechanism, this elastic dissipator mechanism, resists fracture and fatigue. So today I don't have time to get into nuances. This is a whole talk. I think actually many classical important materials such as plastic. Plastic is a very fatigue resistant compared to metal. So here I have a piece of plastic. I don't know if you can see, piece of plastic. It's polypropylene. And you just bend back and forth many times. When I have time, I just bend this. It still doesn't suffer fatigue. Think about a metal. Metal, after 10 times, it breaks. This thing doesn't break because it's a long chain polymer. It's essentially elastic dissipator. So elastic dissipator does not work only for elastomer, also work for plastics, and to some extent work for ceramic matrix composite, because the fiber itself also has that feature. The stress is deconcentrated over long length. Before the crack cut this fiber, the fiber is stored over long distance high stress. Stress is deconcentrated. But once fiber break, the long segment of fiber needs to release energy. That mechanism is a fatigue resistant. So ceramic matrix composite is much more fatigue resistant than other tough materials. So I should not overemphasize this bulk dissipation. It's probably a temporary idea, I think. I now think. I know we spend our time in the group pursuing that idea. The world has hundreds and thousands of people also developing that idea. That idea, using today's phrase, possibly fake news. Elastic discipline.
Thanks.
Yanfei.
Hey, how are you? Zhigang, nice to see you here. As always, this is a great and a fantastic talk. As you can see, there are a lot of your former students. I'm one of your former students. This is Yanfei Gao from University of Tennessee, but I'm different from all the other students. I'm on the screen. I'm probably the only student of yours from 1900s. Right? I'm from last century, and all those students on the screen are from this century. So I only read your papers in last century. I can only understand your papers in the last century. Some papers you wrote with Jimmy, you wrote with Gang Bao, with Wei Yang, and with Qing Ma. So on the fracture and oxidation. So when you actually answer questions by Marva, by Amit, and other people, you mentioned this old knowledge that you wrote with Gang Bao and Jimmy Hsia on this crack size or crack bridging. So when the size, there's always a size under which the floor becomes unimportant. Now, I always have this question. I thought that you explained this to me, but I still don't understand. Now I can understand that when the floors are small, when you do a fracture test, those small floors are not stress concentration or stress razor. They are not a problem. But let's say then the problem because strength controlled, not fracture controlled. But let's say I'm doing this loading a little bit further, but those floors would be like voices. They would grow, just like the Gerson, Rice, Tracy type of thing. And they progressively damage the material. And this damage may eventually fail the material. That's one aspect. The other aspect is you have this damage, you soften the material, you have all kinds of instabilities like shear bands. Don't you think that those things are consequential? They are very consequential for metals. Don't you think they are also consequential for your materials?
Yeah. Yeah. This actually is a very important question, deep question. Now, here's something quite interesting. You already know that. Let's use your knowledge. For example, just compare glass and steel. Compare these two materials, right? And you know glass has a strength,
the strength is very statistical, varies greatly, right? The strength by orders of magnitude. People produce data, we have everyday experience. Of course, we understand what's the reason. The reason is inside glass, you have floors. The floor size are typically bigger than this fractal cohesive length is a length scale. For glass, it's 1 nanometer. So if you have floor more than nanometer, it depends on floor size now. So that's glass. But for steel, the picture is different, right? People can honestly design things according to the strength, because the strength is not a very statistical variable. It's right. It's yeah, within 20%, you're okay. So now, and of course, the interpretation is this length scale, because for steel, this length scale is about a millimeter or centimeter, depending on the hard steel, soft steel, right? So if your floor size is less than that, typically can be less than that, a centimeter or millimeter, then strength is very decent quantity to use. Now, here is what we learned about our material, hydrogels. This length scale is on the order of millimeter to centimeter, kind of like steel. That seemed to be new. People have intuition, right? If you pull a piece of rubber, by the way, for the rubber, natural rubber, that length scale is 50 microns. People knew about that. 50 microns. People didn't know why 50 microns. We didn't know either. We just do measurement. But for hydrogel, it's a millimeter to centimeter.
Yeah. But let's say put it in this way, you have your hydrogel or whatever, your fancy material, but you have a lot of, let's say, a lot of voids lower than your millimeter size bridging zone. So I have a lot of those things. When I do some mechanical loading, those voids eventually would grow. And then you actually degrade your strength later on. Would this be a problem? This is like a damaging process. That's actually for metal, right? Metal, tough metals do not fail by fracture, they fail by void and damage process.
Yeah. Now, there's one thing very special about elastomer and hydrogel. So compared to steel, steel is atomic material. All atoms can change neighbors, which we call plasticity eventually, right? Flow, like liquid. But for elastomer, you have a cross-link. All the bonds are covalent. In principle, they do not break. So voids actually do not break unless you actually break atomic bond. That's the essential difference between elastomer and something like steel.
Yeah. Well, that's certainly very amazing. Thank you.
Yeah, hydrogel is a molecular material. Steel is atomic material. That's a key difference. Essential things I learned from Franz. Franz is a person who made atoms really real to me.
Yeah. Well, that's a very sharp answer. Thank you, Zhigang. Yeah.
Okay, Jia Wei.
Hey, Zhigang.
Yeah.
Hey, everybody. So as a foremost student in Soul Lab, I was very fortunate. I have privilege to learn both theory and experiments from you. So especially one third of my work is about wrinkles and creases, just following the treasure left by Li Hua. And now later on, we're starting working on some hydrogels and adhesion later. So yeah, it's a very good and a very good fortune from Zhigang. So my question is like this. So after working on so many adhesions in the past few years, I'm always thinking about the adhesion's toughness versus adhesion's strength. Which one is the more dominant or more important properties in practical applications? So for example, you have high toughness does not mean you have high strength to break the interface, right? Even if you have a brittle interface, but you have a high strength, then you need more force to break the interface. So I'm thinking which one is more important parameters we need to keep in mind when we design the next new adhesives.
Thank you. Thank you. Oh, by the way, Jiawei is this co-inventor. No, he was the main inventor. I think Robin will agree with that. Of topological adhesion and this whole enterprise. Also, Jiawei wrote, I don't know how many papers you wrote on so many different things, and now you pretend to be a bioengineer. Right? He's still postdoc. Are you looking for a job at some point? Faculty position, is that
next
still
year?
game, right?
Yeah, because we are working on 2 projects right now. So I want to finish those 2 before I'm searching the job market.
Yeah. So yeah, he is available. So if some of you, I know you're in a position to hire people, consider Jiawei seriously, even now. If you wait, he will disappear. The guy is amazing. That's about Jiawei. Jiawei did ask a question about strength and toughness. Of course, we all read this classical paper by great man Rob Ritchie, who gave EML webinar a few weeks back. He had a paper titled, it's a Nature Materials paper titled, "The Conflict Between Strength and Toughness," right? We all know, right? So the conflict existing in particular class materials, such as steel. If you increase strength, typically you limit the amount of plasticity and your toughness become lower. So it's understood for many decades. However, for something like a hydrogel, I think we can do both. So I guess a scientific question is both are important in applications. You actually want to have both. Of course, in particular application, maybe you want to have strength, maybe you want to toughness, but both properties are important and they're distinct. For soft materials, you can actually have high values of both. Because your design space is so enormous. So enormous, yeah. Although strength is related to this, their ratio is related to this fractal cohesive length, right? Yeah. They're both important.
Yeah, so I'm thinking about topological adhesion, for example, using calcium and using cyanoacrylate.
Yeah.
So for example, if you want to advance in the crack in the calcium top here, the interface, the force you may apply only 1 Newton.
Yeah.
But if you want to apply, so you want to advance same crack in the same material, but using cyanoacrylate as the interface, you probably need 8 Newton more.
Mm-hmm.
Even though cyanoacrylate itself is a glassy polymer, it has very low toughness compared to calcium, but you need a lot of force to break the interface. So in this situation, I'm thinking cyanoacrylate may have more advantage in prevent crack propagation, right? Yeah.
Yeah. Yeah, for that application, right? Because you just described application. So for any application, the moment you can guarantee floor size below the material length scale, then toughness become irrelevant, right?
Yeah. Okay.
Yeah, it's a strength. But to guarantee that length to be large enough is essential. That's why glass cannot be in most applications, just because the length is very small. Because glass, in terms of atomic strength, is as high as any material.
Right.
Right.
Yeah. Yeah.
So it's a length. Ultimately, it's a length. You need to guarantee that length first. The way to guarantee length is have a high enough toughness. The moment the toughness provide large enough length, fractal cohesive length, then it's all about strength.
Yes. So some related question is about if you have, for example, softer materials, if you just pull the material apart, even though toughness is high, the force is low, then you can cause tremendous deformation at the interface. This sometimes you need to avoid in the practice, right?
Even before
So,
breaking, yeah.
Yeah. Okay, I see. So it really depends on different applications and the length scale in the interface.
Yeah, however, about this adhesive being soft than the substrate, that actually often is not a problem. For example, we often use epoxy to bond metals.
Yeah.
Epoxy is much softer than metals, but what makes it work is because the metal itself provides stiffness. So as long as the epoxy is very thin, you can use a soft material to bond hard material, still get the same stiffness.
Yes, yeah. I learned it from your fractional mechanics class, still in mind.
Yeah, so I don't know if this guy Tongqing is here or not. Tongqing recently published a paper. We published a joint paper. It's really his idea. That should use a really long chain to bond to soft material. When you have a very long chain itself is not good material. The long chain is very soft.
Yeah.
But if your soft long chain is very thin layer, you can use it to bond soft material. Your stiffness, strength is all the same. No problem.
I see.
It's the same thing as epoxy metals.
Terrific.
Yeah.
Thank you. Perfect.
Okay. Jen Yang.
Hi, Professor Suo. My name is Zhen, and I'm currently a PhD student at McGill University under Professor Jianyu Li. And I was also a master's student of Dr. Tian Tang at the University of Alberta.
Okay.
I saw she has left.
Yeah.
So I have 3 questions, if I could. So my first question is about the rate-dependent adhesion. In one of your slides, you show that the rate-dependent adhesion is a function of the varying crack speed. So in that picture, you clearly show that the adhesion significantly reduced with the decreasing crack speed. So I want to hear some of your comments whether viscous dissipation is more important or it's more energy, the background dissipation, the so-called Mullins effect. Because in principle, if we talk about Mullins effect, it's rate independent, meaning that even at the extremely low crack speed, we should also see damage if we do not consider the self-heating of the hydrogel. So even at the extremely low crack speed, we should still be seeing some hysteresis, and therefore we have the adhesion enhancement. And in your figure, you did extrapolation such that you have an intersection point with the energy axis, and presumably this value is still higher than the fatigue threshold that's characterized by the fatigue test. And again, in many papers, people more often report the adhesion energy at some finite speed. Some common used speed is 0.5 millimeter per second or 1 millimeter per second. In that case, we can get 1,000 joule per meter square. But the intrinsic value now is widely accepted characterized by fatigue threshold is only on the order of tens joule per meter square, and that's about 100 enhancement factor. And then Hugh Brown has a double network hydrogel damage model, and his model actually predicts about 100 enhancement factor. But then if we only consider the Mullins effect, we can put it in the finite element. So this work is pioneered by Professor Zhao Xuanhao and Professor Zhang Chen. But in that case, if we only consider the Mullins effect, we can only get enhancement on the order of maybe 4, on the order of unity. But if we, in that case, but if we compare, in your case, the adhesion that's measured at the lower limit of the velocity with the intrinsic value, it seems that they become consistent because both are on the order of 10 joule per meter square, and we get maybe enhancement of 3 or 4. And this part is actually consistent with our finite element result or some scaling analysis. So this is my first question. My second question is, could you make some comment on the right amount of adhesion energy that's needed for a specific application? In the past few years, people have been pursuing extreme properties of hydrogel adhesive. So the adhesion energy needs to be basically the higher the better. But in some certain applications, for example, if we implant the adhesive in the human body, then the energy release rate or the driving force, it's triggered by maybe the pumping of the heart. So in that case, the energy release rate, the driving force, it might not be as strong as like in the peeling mode. So in that case, we might not need that high amount of adhesion energy. Maybe 10 joule per meter square is enough just for doing the work. And my third question is,
can you limit it to 2?
Yeah, sorry. Okay, I'll just stop here then.
All right. Okay. Your first question is about fatigue threshold. So I don't know if you have seen our paper on fatigue threshold of hydrogels. Have you?
Yes, I read some, yes.
Yeah, I read some. We actually made some serious progress, fundamental progress. So for example, when Ruobing tests our polyacrylamide alginate tough gel, that tough gel has toughness of 10,000, but the threshold is only 50 joule per meter squared. Threshold is very low. Yeah. However, when another student, I don't know if she's here, she's a student in China. When she tests Wenlei Zhang, she tested Jianping Gong's material, double network tough gel. And she found, we also published a paper in engineering fraction mechanics, that toughness is about several hundred joule per meter squared. Okay, so initially it was a surprise, but we resolved that surprise in that paper. The answer is very simple, because in that double network hydrogel, all we did, or Jianping Gong did, it's her material. She did not has the tough adhesion, not adhesion, fatigue. So we did a fatigue and made this discovery. All she did is the chains are extraordinarily long. And once you have a very long chain doesn't suffer fatigue. It's just an elastic dissipator. So the long chain itself is very soft, but she has another network provides stiffness. That's how it works. So yeah, and you're quite right. The fatigue threshold is something important to measure, but you can update your information now. It's possible for hydrogel and elastomer to create a threshold on the order of 10, 100, and even 1,000. Recently, we have a paper of a hydrogel elastomer composite, just soft material, achieve threshold 1,000. Shuanghe also has another system, polyacrylic PBA, polyvinyl acrylate, alcohol, PBA. And that material also achieve, with some processing, achieve fatigue threshold 1,000 joule per meter squared. So it's possible to vastly enhance fatigue threshold. To me, we are on the verge to formulate a plan to win the war against fatigue. I'm serious. Okay, it's just a plan. We haven't won the war yet. Now, your second question about right amount of adhesion energy, you're totally right, of course. Even glass find application, a very brittle material, but it's a window. It find an application because it's transparent and it's very hard. So you're right. Yeah, you need to use toughness, appropriate toughness for your specific applications.
Thank you
It's
very
getting
much.
a little late now. I know I'm sure you asked one question already. How about let me allow Daniel to ask a question or to make some comments. I know Daniel is a plant scientist or plant biologist.
Yeah, hello, Jimmy, hello, Zhigang. Yeah, so I collaborate with Sulin Zhang. I'm at Penn State. I'm a plant biologist, and I'm an interloper on this seminar series. Another great talk here. I've enjoyed it very much, and I wanted to just point out to the audience, who are, I guess, largely engineers and material scientists, that plants face these issues. Plant bodies face a number of issues that are directly related to the topic you were talking about today. So adhesion, and they're of great importance agriculturally. So things like and just for plant biology. So the leaves are starting to fall from trees. That's a case of genetically controlled adhesion between in a very specific layer of cells. One very obvious example in New England, where you are at the moment. The ability of cells to adhere to one another in the plant body is really important for the structural strength of plant tissues and stems, and this also has a potential engineering application, because when you want to convert biomass, cellulosic materials, into, let's say, biofuels, one of the important issues is breaking the cells into little pieces, and that adhesion from one cell to the next is so strong, it's relatively tough to break these things apart. Fruit texture. You've had apples, right? Bite into them. Some of them are nice and crisp. Some of them are mushy, right? That's all adhesion between cells. Many examples where the sort of phenomena you're talking about are really important for plant agriculture, plant products, and plant biology. And a lot of these phenomena are linked to the properties of pectins. So pectins are a lot like alginates that you've talked about. Yeah. They're sugar polymers with carboxyl groups, which can be modified in various ways. But so we know that much, but that's probably not the whole story. There are some protein interactions with the pectins that are probably important. And a point I want to make is the approach you took, that you exemplified in your talk today, that has not really been explored and applied to the plant biology field, where adhesion mechanisms have been investigated. And so I think there's a huge opportunity for people who are interested in these sorts of approaches to apply that sort of knowledge to the plant biology field, and bring in new aspects and new insights into how plants control their physical properties.
Yeah. Thank you, Daniel. Well, Sulin, you have a lifelong of problems waiting for you. Yeah, Daniel is waiting at the end.
You're muted.
You're muted.
Yeah, exactly, Zhigang. I'm such fortunate to have Dan working on Dan many interesting problems in plant cells.
Yeah.
Yeah.
What are you going to
fantastic.
talk about? What are you going to talk about next week?
I don't know if I'm ready to talk about that. We just submitted a paper to science with Dan. And it's very exciting, and Dan fed me with a lot of interesting problems at the boundary of mechanics and biochemistry.
Yeah.
So endless. I'm already hands-full and very excited about that.
Yeah, great.
Yeah.
Yeah.
We have a person from China. Lei Wang. Lei said that I don't know whether it's a female or male, but that person has been waiting there for so long. It's 1:30 in the morning. So why don't we give give you the chance to ask a question. Right.
Okay, thank you, Jimmy, for bringing my question forward, and thank you, Zhigang Suo, and all of you for the excellent discussion about the mechanisms and the other questions. And for me, I learned a lot from this discussion. So we all see that there are so many great works, papers. So I'm wondering about, is there any products? And another question is how to transfer the academic research to practical applications. And that's my two questions. Thank you so much.
Oh, translation, yeah. So Xuanhe has done quite a bit translation in this thing. In my talk, I give one example of his work because he has done so much. So you probably want to take a look at his EML webinar. He gave an EML webinar before Xuanhe Zhao. In my own case, I've been working with a group of people in China, try to develop hydrophilic coating as one application for medical instruments. Because a former student has a startup company making medical instruments. Then hydrophilic coating is still a important problem for him. So yeah, it's a very interesting question. This domain really is looks close to application, but yeah, actually I have another example with an application I'm involved in. I showed a tissue adhesive example. Now I'm working with a group of people in China, former member of the group, Jingda Tang, and also he has a collaboration with medical doctors about using adhesive in surgery. Very interesting problem. I cannot talk about it because they're still in the middle of working on it. But again, the moment I start to work on these things, I know these are not problems for me. Just too many important details that require lots of attention, lots of time, and something I don't have expertise. For these things, I just collaborate with people. People provide attention and provide detailed background knowledge. And we, mechanics people, materials people, know something about materials. So collaboration is crucial. But you're absolutely right. The opportunity is just enormous because I guess the society is ready to integrate human bodies with other things. Just ready.
Yeah, thank you.
Yeah, thank you.
I'm waiting for your further work. Yeah, thank you.
Thank you.
Xuanhe, since your name was mentioned, I know I see. Do you want to make a few comments about translation?
Xuanhe probably is busy with his baby.
Busy with him. Okay. I think we have to stop somewhere.
Yeah.
Sure. Sorry.
Oh, okay.
Oh,
yeah.
How's your baby?
It's great. It's great. It's just
baby,
very
not
tired.
just one baby. Baby one, baby two.
Babies. Yeah. Thank you, Zhigang. So I just want to echo Zhigang's point. So this is a field from both fundamental and applicational aspect. It's just so much we can do, and the impact on both science and the society just beyond imagination. I think this is truly a great field for especially I would say for young students. Please consider this a great opportunity, and the barrier is actually not as high as many other fields. There are lots of problems. You can be leaders, you can be pioneers in subdomains in this emerging field.
Yeah.
Wonderful. Thank you very much, Xuanhe.
Hey, Chen Zhang is here. Chen Zhang is a very important person.
who contributed to
yes.
an important, highly cited EML paper.
Okay, all right. Teng, you want to ask a question or make some comments?
Sure, yeah. Thank you, Professor, for the nice comments, and also thanks, Jimmy, for organizing. Yeah, so it's great, like talk and discussing, and I have a follow-up question about the interface between the biological material and the engineering material. You already showed that how to get a very high like adhesion energy, and but another question is when we integrate the engineering material and the biological material, you will change the environment of biological material. In the long term, you may introduce some damage of the biological material, like the knee replacement. So some people use the cement and bone. In the long term, you will have bone loss. So and also so similar other problem. So I want to hear your vision about the mechanics role, like how mechanics can help like people to get a better stable like interface in the long term.
Yeah. So yeah, very important question. Here, you really need to work with specific applications, but two broad classes we encounter. One is you just need to have a material to serve certain function. For example, during surgery, temporary glue. What you want is either you remove it or degrade it. So there are a lot of demonstrations in the past. Now what we can do is enhance adhesion when you use it, but still allow it to degrade. Then biocompatibility is less of an issue. But for something like knee, that has to be permanently there, or some stent you need to put into the body, that's still an open problem. But for example, for stent, people had decades of experience now. The device stay in the body. Essentially, you need to have a blood thinner, right? Yeah. So individual problem you need to solve, often not really solved by mechanics or even materials. It's solved through biochemistry. Yeah, you just need to work with these people. But there are plenty of examples to provide us with good perspectives in the field.
Okay.
Yeah.
All right. It's been 3 hours, 10 minutes.
Jimmy, for you, it's 1:40, right?
1:40 in the morning. I'm barely awake.
Sorry, Jimmy, thank you for doing that. This is what you need to stand for.
Sure. Great talk, Zhigang. Thank you so much. Let's all thank Zhigang again for this wonderful, wonderful talk.
Thank you, Jimmy.
Okay.
All right.
We'll see you next week.
See you next week for Suling. Another wonderful talk.
Bye-bye, guys. Pressure song. Okay. Bye-bye.
Bye.